Dear listener, tonight I want to tell you about something happening right now, 43 million miles above your head, something that shouldn't exist, yet glows green in the darkness of space as it races toward Mars at 25,000 miles per hour. They call it 3I Atlas, the third confirmed visitor from beyond our solar system. But this isn't just another piece of cosmic debris tumbling through the void. No. This ancient wanderer carries chemistry from a star system that died before our sun was born. Ice and dust, 7 billion years old, frozen since the dawn of time itself. Here's what haunts every astronomer watching this convergence. Mars, a world that has remained essentially unchanged for millions of years, is suddenly alive with atmospheric disturbances, oxygen spikes that shouldn't happen, methane bursts that have no explanation, chemical signatures that mirror, almost perfectly, the strange green glow of our interstellar visitor. The timing is mathematically impossible to ignore. These changes began precisely when Atlas entered our solar system. Not before, not after, exactly when this ancient chemistry from another world crossed into our cosmic neighborhood. Scientists don't like coincidences. They especially don't like coincidences involving dead planets suddenly showing signs of, well, something that resembles resurrection. Mars hasn't changed significantly in 4 billion years. Until now. So tonight, as Atlas continues its approach toward the red planet, we're left with a question that keeps researchers awake in observatories around the world. A question whispered in the halls of NASA, debated in classified meetings, and discussed in hushed tones wherever people study the movements of worlds. What is this 7 billion-year-old visitor doing to Mars? Mars has been sleeping for 4 billion years. Not the kind of sleep we know, but something deeper. The sleep of a world that once had rivers and oceans, an atmosphere thick enough to breathe, seasons that brought gentle rains across vast continents. All of that ended long ago. Mars lost its magnetic field. Its atmosphere leaked away into space. The planet grew cold, thin, silent. For centuries, we've watched Mars through telescopes and seen the same story. Dust storms that circle the globe like clockwork. Ice caps that grow and shrink with predictable seasons. Thin air that barely registers on our instruments. The red planet follows patterns carved in stone over geological time. Nothing surprises us about Mars anymore. Our rovers crawl across its surface, taking measurements that confirm what we already know. The same atmospheric pressure readings, the same chemical signatures in the soil, the same cold, dry winds that have blown unchanged since before humans walked the Earth. Mars is stable. Mars is predictable. Mars is, by every measure that matters, dead, until July 1st, when everything began to change. It was a Tuesday morning in Chile, when the Atlas telescope first spotted something unusual. Atlas stands for Asteroid Terrestrial Impact Last Alert System, and its job is simple: scan the skies for objects that might threaten Earth. The telescope sits high in the Atacama Desert, where the air is thin and the night sky burns with stars. Every few minutes it captures images of space, comparing them to previous images, looking for dots of light that move against the star field. That morning, Dr. Maria Santos was reviewing the night's observations when she noticed something that shouldn't exist. A fast-moving speck of light racing through the constellation Sagittarius at impossible speed. Too fast for any asteroid, too bright for debris. The computer had flagged it automatically, marking it with the temporary designation A11PL3Z. Within hours, telescopes around the world turned their attention to this mysterious object. The numbers they collected told an incredible story. This wasn't just another piece of space rock. The visitor was traveling at over 60 miles per second relative to our sun. That's fast enough to cross the entire United States in less than 2 minutes. No object born in our solar system could move that fast, unless something had accelerated it to incredible speeds. More importantly, when astronomers traced the object's path backward through space, accounting for the gravitational pull of every planet and star it had encountered, they discovered something remarkable. The trajectory pointed to empty space between the stars. This visitor had been traveling for millions, possibly billions of years through the cosmic void between star systems. They named it 3I Atlas. The 3I marked it as the third confirmed interstellar object ever detected. The first had been Oumuamua in 2017. a strange cigar-shaped rock that tumbled end over end as it passed through our solar system. The second was Borisov in 2019, a comet trailing gas and dust from ice formed around a distant star. Now Atlas joined this exclusive club of cosmic wanderers, carrying chemistry from somewhere else entirely. But as telescopes tracked Atlas through July and August, something unexpected began happening on Mars. The first signs were subtle. Rovers on the Martian surface detected tiny fluctuations in atmospheric pressure. Instruments that had recorded steady readings for years suddenly registered brief spikes in oxygen levels. Nothing dramatic. Nothing that couldn't be explained by dust devils or seasonal changes. Then the methane appeared. Mars produces small amounts of methane gas naturally, probably from geological processes deep underground. We've known this for years. But in August, as Atlas continued its approach toward the inner solar system, the methane readings on Mars began to climb. Not gradually, as we'd expect from normal planetary processes, but in sudden bursts that matched no known pattern. The timing was unsettling. Every major atmospheric anomaly on Mars corresponded almost exactly to Atlas's position in space. When the interstellar visitor crossed specific orbital distances, Mars responded. When Atlas brightened as solar radiation heated its ancient ice, Mars showed corresponding changes in its own atmospheric chemistry. Mission controllers at NASA's Jet Propulsion Laboratory began holding quiet meetings. Data from multiple rovers and orbital instruments confirmed the same impossible correlation. Mars, which had remained essentially unchanged for millions of years, was suddenly producing atmospheric signatures that mirrored the chemistry of an object 40 million miles away. The oxygen spikes were the most troubling. Mars' atmosphere is thin, composed mostly of carbon dioxide with traces of nitrogen and argon. Oxygen exists there, but in tiny amounts, produced mainly when ultraviolet light breaks apart carbon dioxide molecules. The process is well understood. It follows predictable patterns tied to seasons and solar radiation. But these new oxygen bursts followed no known pattern. They appeared suddenly, lasted for hours or sometimes days, then vanished. Chemical analysis showed they contained isotope ratios that didn't match normal Martian atmospheric processes. The oxygen seemed to be coming from somewhere else, produced by chemistry that shouldn't exist on Mars. Scientists don't like mysteries. They especially don't like mysteries involving dead planets showing signs of unexpected activity. Mars had been thoroughly studied, mapped, and analyzed. We understood its history, its geology, its atmospheric processes. The planet held few secrets from our instruments. Yet here was Atlas, an ancient visitor from another star system, apparently triggering responses in Martian atmospheric chemistry that defied everything we knew about planetary science. The correlation was too precise to ignore, too consistent to dismiss as coincidence. As summer turned to autumn, the anomalies grew stronger. Mars began producing not just oxygen and methane, but trace amounts of other gases, compounds that suggested active chemistry at work beneath the planet's surface, changes that seemed to pulse in rhythm with Atlas's approach, as if the ancient comet carried some invisible influence that reached across millions of miles of empty space. The question whispered in research facilities around the world was simple, yet terrifying in its implications. How could a 7-billion-year-old visitor from another star system influence the atmosphere of a planet it had never touched? To understand what Atlas might be doing to Mars, we first need to understand what Atlas actually is. And that story begins not millions but billions of years ago, in a part of our galaxy we've never seen up close before. Atlas is old, impossibly old. When astronomers first calculated its trajectory and chemical signature, they discovered something that challenged everything we thought we knew about cosmic visitors. Based on its movement through space and the region of the galaxy it came from, Atlas is likely between 7 and 11 billion years old. To put that in perspective, our entire solar system is only 4.5 billion years old. Atlas was already ancient when our sun was just a swirling cloud of gas and dust. This visitor didn't come from our cosmic neighborhood. It originated in what astronomers call the thick disk of our galaxy, a band of the Milky Way's most ancient stars that formed when the universe was young. These are stars with different chemistry than our sun, stars that formed when the galaxy contained fewer heavy elements. when the cosmic environment was fundamentally different from what we know today. When Atlas was born around one of these ancient stars, the conditions were unlike anything in our modern solar system. The parent star had lower levels of what astronomers call metals, elements heavier than hydrogen and helium. This means Atlas formed in a protoplanetary disk with chemistry we've never directly observed. Its ice and dust carry the chemical fingerprint of stellar conditions that existed before our sun was even conceived. For billions of years, Atlas traveled through the dark spaces between stars. It survived gravitational encounters with other stellar systems, close passes by massive objects that could have torn it apart, and the slow decay of radioactive elements in its core. Through all of this, it preserved its ancient chemistry like a time capsule from the early galaxy. When Atlas finally entered our solar system in July, it brought with it compounds and isotope ratios that don't exist anywhere else in our cosmic neighborhood. Spectroscopic analysis reveals carbon dioxide ice, water ice, and organic compounds formed under conditions that vanished from the galaxy billions of years ago. It's like finding a preserved sample from a world that no longer exists. The comet is also surprisingly large. Early estimates suggest Atlas may be up to 6 miles across at its widest point, making it potentially 10 times larger than 2I Borisov, the previous record holder for largest known interstellar visitor. This size means Atlas carries substantial mass, enough to exert gravitational and electromagnetic influences across surprising distances. As Atlas approached the inner solar system, solar radiation began warming its ancient ice. The process is called sublimation, frozen compounds turning directly from solid to gas without becoming liquid first. But this isn't ordinary sublimation. The ice sublimating from Atlas contains chemistry that hasn't been active for billions of years. Compounds that formed around a star we've never seen, in conditions we've never directly studied. When these ancient compounds vaporize, they create Atlas's distinctive green glow. The color comes from diatomic carbon and cyanogen, molecules that form when carbon-rich ice sublimates in the vacuum of space. But the specific shade of green, the intensity of the glow, and the way it changes as Atlas moves through different regions of our solar system suggest chemistry more complex than anything we've seen in comets from our own neighborhood. This is where Mars enters the story. For billions of years, Mars has maintained what scientists call baseline atmospheric conditions. The planet's thin atmosphere consists of 95% carbon dioxide, with small amounts of nitrogen, argon, oxygen, and trace gases. These percentages vary slightly with seasons and dust storms, but the variations follow predictable patterns that we've mapped and understood for decades. Mars produces oxygen through well-known processes. Ultraviolet light from the sun breaks apart carbon dioxide molecules, freeing oxygen atoms that can combine to form molecular oxygen. The amount of oxygen produced this way depends on solar radiation levels, atmospheric density, and seasonal factors. We can predict these oxygen levels with mathematical precision. The planet also produces small amounts of methane, probably from geological processes deep underground. Rock formations containing organic compounds can release methane when they're heated or fractured by seismic activity. Some researchers think the methane might come from living microorganisms, but geological explanations are more widely accepted. Either way, methane production on Mars follows patterns we can measure and predict. Atmospheric pressure on Mars averages about 6 millibars, less than 1% of Earth's atmospheric pressure. This thin air creates weather patterns we understand well. Dust devils spiral across the surface following temperature differentials. Global dust storms develop when solar heating creates pressure differences between regions. Ice clouds form in the thin atmosphere following predictable seasonal cycles. Chemical composition of the Martian atmosphere has remained stable within known ranges for the entire period we've been able to measure it. Rovers on the surface carry instruments that sample atmospheric chemistry continuously. Orbital spacecraft monitor the planet's atmosphere from above. Multiple international missions provide overlapping data that confirms atmospheric stability. Until Atlas arrived, these baseline readings showed the same story everywhere on Mars. The atmosphere was thin, cold, and chemically inactive. Oxygen levels stayed within expected ranges. Methane appeared in trace amounts following seasonal patterns. Atmospheric pressure fluctuated predictably with temperature changes and dust storm activity. But Mars isn't just chemically stable, it's magnetically dead. The planet lost its global magnetic field billions of years ago, probably when its core cooled and stopped generating the dynamo effect that creates planetary magnetism. Without a magnetic field, Mars can't protect its atmosphere from solar wind, charged particles streaming from the sun that strip away atmospheric molecules over geological time. This magnetic weakness makes Mars particularly vulnerable to external influences. Objects with strong electromagnetic signatures can potentially affect Martian atmospheric chemistry in ways that would be impossible on magnetically protected planets like Earth. The planet's thin atmosphere and lack of magnetic shielding create conditions where small external influences might produce measurable effects. Atlas carries more than just unusual chemistry. As a large active comet, it generates its own magnetic field through the interaction between solar wind and the charged particles in its coma, the cloud of gas and dust surrounding its nucleus. This magnetic field extends far beyond the visible comet, creating what scientists call a magnetosphere that can stretch for millions of miles through space. When Atlas's magnetosphere encounters the solar wind, it creates electromagnetic effects that propagate throughout the solar system. These effects are subtle but measurable, detectable by sensitive instruments designed to monitor space weather and planetary magnetic environments. The timing of Mars' atmospheric anomalies suggests these electromagnetic effects might be reaching the red planet. Every major spike in Martian oxygen levels, every unexpected methane burst, every atmospheric disturbance has occurred when Atlas occupied specific positions relative to Mars and the Sun. The correlations are too precise to ignore, too consistent to dismiss as coincidence. What makes this even more intriguing is that Atlas's ancient chemistry might be uniquely suited to influence Mars. Both objects formed under low metal conditions. Mars in our early solar system, Atlas around an ancient metal-poor star. They share certain chemical signatures that might create resonant effects when Atlas's electromagnetic field interacts with Mars's exposed atmosphere. The question that keeps planetary scientists awake at night is whether we're witnessing the first confirmed case of one cosmic object actively influencing another across millions of miles of empty space. Whether ancient chemistry from the early galaxy is somehow awakening dormant processes on a world that has slept for billions of years. As Atlas continues its approach toward Mars, these baseline atmospheric readings continue to climb beyond anything we've seen before. The first person to notice the pattern was Dr. Jennifer Walsh, a planetary atmospheric scientist at the University of Colorado. She wasn't looking for connections between Atlas and Mars. She was simply doing her job, analyzing routine atmospheric data from NASA's MAVEN orbiter as it circled the red planet, measuring the same thin air that had remained unchanged for millions of years. On August 15th, something in the data made her pause. A spike in oxygen levels that appeared at exactly 3:17 in the afternoon, Mars local time. Not a dramatic spike, barely detectable above normal background levels, but it was there, sharp and clear in the spectroscopic readings. More importantly, it lasted exactly 4 hours and 23 minutes before returning to baseline levels. Walsh had been studying Mars' atmosphere for 12 years. She knew the patterns. She understood the seasonal variations, the daily fluctuations caused by temperature changes, the minor disruptions from dust devils and regional weather. This oxygen spike fit none of those patterns. It appeared suddenly, held steady at elevated levels, then vanished as if someone had turned off a switch. She might have dismissed it as instrumental error, but something nagged at her. The timing. August 15th was the same day Atlas had crossed a specific orbital distance from Mars. Exactly 42 million kilometers. Walsh pulled up Atlas tracking data and compared it to the atmospheric readings. The correlation was immediate and undeniable. Every major atmospheric anomaly detected on Mars over the previous month had occurred when Atlas occupied specific positions in its trajectory toward the inner solar system. Not approximate positions, exact positions down to the kilometer. When Atlas reached 38 million kilometers from Mars, oxygen levels spiked. When it crossed 45 million kilometers, methane readings jumped. When solar radiation heated Atlas enough to increase its outgassing rate, Mars responded within hours with corresponding atmospheric changes. Walsh spent 3 sleepless days verifying the correlation. She cross-referenced data from multiple Mars missions, MAVEN's atmospheric measurements, Curiosity rover's ground-based readings, the European Mars Express orbital data, even archived information from older missions. Every dataset told the same impossible story. Mars was responding to Atlas in real time, across 40 million miles of empty space. The oxygen spikes were the most dramatic anomaly. Under normal conditions, Mars produces oxygen through photodissociation, solar ultraviolet light breaking apart carbon dioxide molecules in the thin atmosphere. This process follows predictable patterns tied to solar radiation levels and seasonal atmospheric density changes. But the new oxygen bursts followed no natural pattern. They appeared suddenly during Mars nighttime, when photodissociation should be at its lowest levels. They contained isotope ratios that didn't match normal Martian atmospheric chemistry. Most puzzling, they seemed to originate not from the upper atmosphere where solar radiation is strongest, but from deeper atmospheric layers where oxygen production through known processes should be minimal. Chemical analysis revealed something even more troubling. The excess oxygen contained trace amounts of compounds that suggested active chemistry, reactions occurring in real time, rather than simple gas release from stored reservoirs. It was as if something was actively producing oxygen in the Martian atmosphere using processes that shouldn't exist on a geologically dead planet. The methane bursts were equally mysterious. Mars had been producing small amounts of methane for years, probably from deep geological processes, or possibly from microbial activity in subsurface environments. But these new methane releases dwarfed anything previously detected. They appeared in massive bursts that raised atmospheric methane levels by orders of magnitude, then dissipated over days or weeks. More disturbing was the chemical signature of this methane. Analysis showed it contained organic compounds that suggested biological processes, complex carbon chemistry that typically forms only in the presence of living systems. But Mars was supposed to be sterile, unable to support the kind of biological activity that produces complex organic methane. When Walsh presented her findings to NASA's Mars exploration program, the response was immediate and divided. Half the scientific team insisted the correlations were coincidental, that Mars was experiencing normal geological activity that happened to coincide with Atlas's approach. The other half demanded immediate expansion of atmospheric monitoring to confirm or disprove the connection. Dr. Robert Harrison from the Jet Propulsion Laboratory represented the skeptical view. Harrison had spent 20 years studying Mars atmospheric chemistry and had never seen anything like sustained external influence on planetary atmospheric processes. In his assessment, the correlations were interesting but meaningless. Correlation doesn't imply causation, Harrison argued during heated teleconferences with the Mars science team. We're seeing normal atmospheric variability that happens to coincide with an interesting astronomical event. Mars has been producing oxygen and methane for years. There's no known physical mechanism by which a comet 40 million miles away could influence atmospheric chemistry on another planet. Harrison's position represented mainstream planetary science. No peer-reviewed research had ever documented one cosmic object influencing atmospheric processes on another world across such distances. The physics simply didn't support the possibility. Gravitational effects fell off too rapidly with distance. Electromagnetic influences required direct contact between magnetic fields. There was no precedent for the kind of long-range atmospheric manipulation Walsh's data seemed to suggest. But Dr. Michael Chen from Stanford's Space Physics Laboratory disagreed. Chen specialized in electromagnetic interactions between cosmic objects and had published research on how solar wind affects planetary atmospheres. In his view, the Mars-Atlas correlation represented a previously unknown form of electromagnetic resonance between objects with compatible magnetic signatures. We're dealing with an interstellar object carrying magnetic field, signatures from a completely different stellar environment. Chen explained during emergency science meetings convened to address the anomaly. Atlas formed around a star with different magnetic field characteristics than our Sun. It's possible the comet's electromagnetic environment creates resonance effects with Mars that we've never encountered before. Chen's hypothesis centered on the idea that Atlas's ancient magnetic signature might be uniquely compatible with Mars's geological electromagnetic patterns. Both objects formed under what astronomers call low metallicity conditions. Mars in our early solar system, Atlas around an ancient star with different chemistry. This shared characteristic might create electromagnetic harmonics that propagate across space when the objects reach specific orbital alignments. The theory was speculative, but it offered a testable explanation for the observed correlations. If Chen was correct, the atmospheric anomalies should intensify as Atlas approached Mars, following predictable patterns based on electromagnetic field strength and orbital mechanics. If Harrison was correct, the correlations should eventually break down as normal atmospheric processes reasserted themselves. As August progressed into September, the data began supporting Chen's hypothesis. The atmospheric anomalies not only continued but intensified precisely as predicted by electromagnetic resonance calculations. Every time Atlas crossed orbital positions that strengthened electromagnetic coupling with Mars, atmospheric activity increased proportionally. More troubling was the discovery of new atmospheric compounds that had never been detected on Mars before. Trace gases that suggested complex chemical reactions occurring in real time, organic molecules that implied biological processes, despite the planet's apparent sterility, chemical signatures that matched, in disturbing detail, the spectroscopic profile of compounds sublimating from Atlas's ancient nucleus. By early September, even Harrison had to acknowledge that something unprecedented was happening. Mars was producing atmospheric chemistry that matched the emissions profile of an interstellar visitor 40 million miles away. The timing was too precise, the correlations too consistent, the chemical matches too exact to dismiss as coincidence. But acknowledging the correlation didn't resolve the mystery. If anything, it deepened the questions. How could ancient chemistry from another star system influence atmospheric processes on Mars? What kind of physical mechanism could propagate chemical effects across millions of miles of empty space? Most disturbing of all, what would happen to Mars when Atlas reached its closest approach in October? The mathematical precision of the correlations suggested something more than random chance. Atlas seemed to be awakening processes on Mars with clockwork regularity, as if the ancient visitor carried some kind of chemical key that unlocked dormant systems in the Martian atmosphere. As September advanced and Atlas continued its relentless approach toward Mars, one thing became undeniably clear. We were witnessing something that shouldn't be possible, according to everything we thought we knew about planetary science. The question was no longer whether Atlas was influencing Mars, but how, and what it meant for our understanding of how worlds interact across the vast emptiness of space. Long before telescopes revealed Mars as a world of dust and ice, ancient peoples watched the red planet move across the night sky and told stories that haunt us today. Stories that speak of a world in turmoil, of sky visitors bringing change, of cosmic forces awakening sleeping powers that could reshape entire worlds. Mars troubled the ancients in ways other planets didn't. While Venus shone with steady beauty and Jupiter moved with dignified grandeur, Mars flickered. It brightened and dimmed unpredictably. It changed color from orange to deep red to blood-bright crimson. Sometimes it moved forward through the stars. Sometimes it stopped. Sometimes it reversed direction entirely in what astronomers now call retrograde motion. To the Romans, Mars was more than just a wandering light in the heavens. He was Martius, the god of war, the protector of Rome, the divine force who fathered Romulus and Remus, the twin founders of their empire. But Mars wasn't simply a god of destruction. He was also the guardian of agriculture, the force who brought both conflict and fertility to the world. This duality puzzled Roman priests and poets. How could the same divine power govern both the blood-soaked battlefield and the peaceful farmer's field? Ancient Roman texts describe Mars as having two faces. In spring, he was the agricultural protector who blessed the planting season. March, the month named for him, marked the beginning of both farming and military campaigns. But in autumn, when the harvest was complete and armies prepared for war, Mars revealed his fiercer aspect, the raging god whose fury could shake the foundations of the world. The Romans believed Mars carried a sacred spear that was kept in the former residence of their kings. This spear, they said, would tremble whenever Rome faced danger. Historical accounts claim it vibrated ominously before Julius Caesar's assassination, before great military defeats, before plagues and disasters. The spear seemed to connect Mars directly to events on Earth, as if the god could reach across space to warn or threaten those under his protection. But the Romans weren't the only ancient people who saw something disturbing about Mars. Indigenous cultures around the world developed remarkably similar stories about the red planet and visitors from the sky. The Lakota people of North America called Mars Firestar and told stories of a time when it grew so bright it could be seen during daylight hours. Their oral traditions speak of a period when Firestar danced across the sky for many nights, growing larger and brighter until it seemed to touch the earth. During this time, their ancestors reported strange phenomena, unusual animal behavior, unexplained lights in the sky, dreams and visions that seemed to come from somewhere beyond the normal world. According to Lakota elder Joseph Horn, whose great-grandfather lived through what he called the time of the angry star, the red planet's brightening coincided with mysterious changes on Earth. Springs that had flowed clear for generations suddenly turned red. The aurora appeared far south of its normal range. Animals behaved strangely, as if responding to signals humans couldn't detect. Similar stories appear in the oral traditions of the Maya. Their astronomical texts describe Mars as No Ek, the great star, and record periods when it became restless and changed the natural order of things. Mayan stone carvings show Mars in conjunction with other celestial symbols during times they describe as sky-earth turnings, cosmic events that brought transformation to the world below. The Maya were precise astronomers who tracked planetary cycles with mathematical accuracy. Their codices contain detailed records of Mars's orbital patterns going back centuries. But interwoven with these astronomical observations are stranger accounts of times when Mars seemed to influence earthly events directly. They describe periods when the red planet's approach coincided with unusual weather patterns, strange lights in the sky, and what they call spirit winds that carried unfamiliar scents and sounds. Aboriginal Australian cultures have some of the world's oldest continuous astronomical traditions, stretching back over 40,000 years. Their Dreamtime stories include accounts of Warumbu, the Red Wanderer, who occasionally grows restless and sends messages to Earth through light and colour changes that can affect the spiritual world of their ancestors. The Wardaman people of Northern Australia tell of a time when Warumbu came so close to Earth that it sang to their ancestors through the ground itself. During this period, they say, sacred sites across the continent began exhibiting unusual phenomena. Rocks that hummed with low sounds, water sources that changed colour, and animal behaviour patterns that disrupted traditional hunting and gathering cycles. These indigenous accounts share disturbing similarities despite emerging from cultures separated by thousands of miles and thousands of years. They consistently describe Mars as having the ability to influence earthly events when it reaches certain positions or brightness levels. They speak of the red planet as more than just a light in the sky, as a force capable of reaching across space to touch the world below. Even more intriguing are ancient Chinese astronomical records that describe Mars during what they call great approaches. Chinese court astronomers who maintained detailed observations for over 2,000 years recorded periods when Mars appeared unusually large and bright. During these times, they document unusual atmospheric phenomena, strange cloud formations, unexpected auroras, and what they describe as sky fire that appeared without storms or other natural causes. The Chinese texts are particularly specific about timing. They note that these atmospheric disturbances began precisely when Mars reached certain positions relative to Earth and other planets. The correlation was so consistent that Chinese astronomers developed prediction methods based on Mars's orbital position. allowing them to forecast periods when unusual sky phenomena might occur. But perhaps the most troubling ancient accounts come from cultures that describe sky visitors arriving during Mars's bright approaches. Sumerian texts speak of the Anunnaki, beings from the heavens who came to Earth when Nergal, their name for Mars, burned bright in the night sky. These visitors, according to the texts, possessed knowledge of astronomy and engineering that exceeded human understanding. The Sumerian accounts describe the Anunnaki as arriving in what sound remarkably like spacecraft, bright boats that traveled the sky and could move between Earth and other worlds. More significantly, the texts consistently link these visitations to periods when Mars appeared unusually large and active in the night sky. Native American traditions across multiple tribes describe similar sky visitors who arrived during times when the firestar grew bright. The Hopi speak of the star people who came from the direction of the red star during ancient times, bringing knowledge of astronomy and agriculture. The Cherokee tell of beings of light who appeared when Mars danced close to Earth, teaching their ancestors about the connection between sky and Earth, between the movements of worlds and the cycles of life below. These stories might be dismissed as primitive misunderstanding of natural phenomena, except for one disturbing detail. Many of these ancient cultures describe the sky visitors as bringing changes to Earth's atmosphere and weather patterns. They speak of times when the air itself seemed different, when breathing became easier or harder, when plants grew differently, when the very chemistry of the world appeared altered. The Aboriginal Australians describe periods when the air spirits changed during Warrumboo's close approaches, affecting not just human consciousness, but the growth patterns of plants and the behavior of animals. The Maya recorded atmospheric changes that coincided with Noach's bright periods, describing alterations in rainfall patterns and the appearance of new types of clouds. What makes these ancient accounts particularly unsettling is how closely they parallel the current Atlas situation. Here we have an interstellar visitor approaching Mars, just as Mars is showing unprecedented atmospheric activity. Ancient cultures consistently associated such cosmic convergences with earthly changes that they attributed to visitors from the sky. Modern science tells us these ancient stories are mythology, folklore, primitive attempts to explain natural phenomena without the benefit of scientific knowledge. But as Atlas approaches Mars and the red planet responds with atmospheric changes that mirror the chemical signature of our cosmic visitor, we have to ask ourselves a troubling question. What if the ancients weren't describing mythology at all? What if they were recording real events, cosmic interactions between worlds and visitors that our modern science is only now beginning to detect? The ancient stories speak of sky visitors bringing change during times when Mars grew bright and active. Today, as Atlas carries 7 billion years of ancient chemistry toward the red planet, Mars is displaying atmospheric activity unlike anything in recorded history. The timing, the chemical correlations, the electromagnetic effects, all echo the patterns described in stories that predate written history. Perhaps the ancients weren't telling myths about gods and spirits. Perhaps they were keeping careful records of previous cosmic encounters, preserving knowledge of what happens when visitors from the deep places between stars draw close to the worlds we call home. As Atlas continues its approach toward Mars, those ancient stories whisper a question that modern science isn't ready to answer. How many times has this happened before? To understand what Atlas might be doing to Mars, we first need to understand how we watch the red planet's atmosphere in the first place. The methods we use are both remarkably sophisticated and surprisingly simple. A combination of instruments scattered across the surface of Mars and orbiting high above, all working together to create a complete picture of a world 40 million miles away. The story begins with robots on the ground. NASA's Curiosity rover has been wandering the Martian surface since 2012, carrying what amounts to a sophisticated weather station called REMS, the Rover Environmental Monitoring Station. REMS looks like a small collection of booms and sensors extending from Curiosity's mast, but it's actually one of the most sensitive atmospheric monitoring systems ever built for another world. Every day, REMS measures atmospheric pressure, temperature, humidity, wind speed and direction, and ultraviolet radiation levels. The pressure sensor can detect changes as small as 1 pascal, roughly the pressure difference you'd feel between the ground floor and second floor of a building. For Mars, where the entire atmosphere exerts less pressure than a gentle breeze on Earth, this sensitivity is extraordinary. The temperature sensors work by measuring infrared radiation, the heat that every object gives off simply by existing. Mars is cold, averaging about -80 degrees Fahrenheit, but these sensors can detect temperature changes as small as a few degrees. They take measurements continuously, creating a detailed record of how Mars heats and cools throughout each sol, the Martian day that lasts 24 hours and 37 minutes. But perhaps the most important sensor for understanding the current atmospheric anomalies is REMS's humidity detector. Mars is an extremely dry world. On most days, the relative humidity hovers near zero. When REMS suddenly started detecting humidity spikes corresponding to Atlas's position, it marked the first time we'd ever seen Mars's atmosphere respond to external influences in real time. The wind sensors use a technique called hot film anemometry. They heat tiny wires to a specific temperature, then measure how much power it takes to keep them hot as Martian air flows past. Moving air carries heat away faster than still air, so changes in power consumption reveal wind speed and direction. The system is sensitive enough to detect breezes as gentle as 3 miles per hour. Important on a world where the thin atmosphere makes even strong winds feel like whispers. High above these surface instruments, a fleet of spacecraft orbits Mars, watching the planet's atmosphere from space. The most important for our current mystery is MAVEN, the Mars Atmosphere and Volatile Evolution mission. MAVEN carries instruments designed specifically to study how Mars loses its atmosphere to space, but they're equally good at detecting sudden atmospheric changes. MAVEN's mass spectrometer acts like an extremely sensitive nose, sniffing the upper atmosphere and identifying every gas present down to incredibly small concentrations. When oxygen levels began spiking in correlation with Atlas's approach, MAVEN detected not just the increased oxygen, but the specific isotope ratios that told scientists this wasn't normal atmospheric oxygen production. The European Space Agency's Mars Express orbiter adds another layer to our observation network. Mars Express carries a spectrometer called PFS, the Planetary Fourier Spectrometer, that can identify atmospheric gases by analyzing how they absorb different wavelengths of sunlight. When Mars Express detected the same oxygen and methane anomalies that ground-based instruments were recording, it provided crucial confirmation that these weren't just local effects, but planet-wide phenomena. To understand how these instruments actually work, imagine trying to identify the ingredients in a soup by smelling it. Your nose detects different molecules, and your brain interprets those signals to identify garlic, onion, herbs, and so on. Spectroscopy works the same way, but instead of smell, it uses light. Every molecule absorbs and emits light at specific wavelengths, its unique optical fingerprint. Water vapor absorbs certain wavelengths of infrared light. Carbon dioxide has its own distinct pattern. Oxygen, methane, and hundreds of other compounds each have signatures as distinctive as human fingerprints. When sunlight passes through Mars's atmosphere, molecules in that thin air absorb some wavelengths while letting others pass through. By analyzing which wavelengths are missing from sunlight after it passes through the atmosphere, scientists can determine exactly which gases are present and in what concentrations. This technique is so sensitive that it can detect gas concentrations measured in parts per billion. On Earth, that would be like identifying a single drop of food coloring in a swimming pool. On Mars, with its much thinner atmosphere, the sensitivity is even more remarkable. The real-time monitoring system that tracks these measurements operates continuously, 24 hours a day, 7 days a week. Data flows from Mars rovers and orbiters to NASA's Deep Space Network, massive radio dishes in California, Spain, and Australia that stay in constant communication with spacecraft throughout the solar system. Every few minutes, atmospheric readings from Mars arrive at NASA's Jet Propulsion Laboratory in Pasadena, where computers automatically compare them to baseline measurements and flag any anomalies. During normal operations, Mars atmospheric data is routine, predictable, almost boring. The same pressure readings, the same gas concentrations, the same temperature patterns that have persisted for years. But since Atlas entered our solar system, these monitoring systems have been working overtime. The anomaly detection algorithms began triggering alerts multiple times per day as atmospheric readings diverged from normal patterns. Scientists who had grown accustomed to stable data suddenly found themselves staring at measurements that made no sense according to everything they knew about Mars' atmospheric chemistry. The most puzzling aspect of the current anomalies is their precision. When Atlas reaches specific orbital positions, Mars responds within hours. When Atlas's outgassing rate increases due to solar heating, corresponding changes appear in Mars' atmospheric chemistry with clockwork regularity. The correlation is so exact that scientists have begun using Atlas's position to predict when Mars' atmospheric anomalies will occur. This predictive capability reveals something extraordinary about our monitoring systems. They're sensitive enough to detect atmospheric changes that correspond to events happening 40 million miles away. The instruments can measure not just the presence of unusual gases, but their precise timing, their chemical signatures, their distribution patterns across the planet. Temperature mapping from orbit shows that the atmospheric anomalies aren't uniform across Mars. They appear first in the planet's northern hemisphere, then spread southward over hours or days. This pattern suggests the effects propagate through Mars's atmosphere like waves, originating from a specific source and spreading outward. The spectroscopic analysis reveals even more disturbing details. The excess oxygen contains isotope ratios that don't match normal Mars atmospheric chemistry. The methane shows organic compounds that suggest biological processes, despite Mars's apparent sterility. Most troubling, some of the detected gases match the exact chemical signature of compounds sublimating from Atlas's nucleus. Ground-penetrating radar aboard. Mars Express has detected unusual electromagnetic activity in the planet's subsurface that correlates with the atmospheric anomalies. These signals suggest geological processes awakening deep beneath Mars's surface, processes that have been dormant for millions of years. The precision of these measurements allows scientists to track not just what's happening to Mars's atmosphere, but exactly when and how it's happening. They can measure the rate at which unusual gases are being produced, the depth in the atmosphere where they originate, the speed at which they spread across the planet. What emerges from all this data is a picture of Mars responding to Atlas's approach in ways that our instruments can measure, but that our theories struggle to explain. The red planet, which has remained essentially unchanged for millions of years, is suddenly producing atmospheric chemistry that mirrors an interstellar visitor 40 million miles away. As Atlas continues its approach toward Mars, these sensitive instruments continue recording every subtle change in the planet's atmosphere. They're providing us with unprecedented real-time observation of what might be the first confirmed case of one cosmic object influencing atmospheric processes on another world across millions of miles of empty space. The question that haunts every scientist monitoring these readings is simple. If our instruments can detect these impossible correlations, what does that tell us about the true nature of the connection between Atlas and Mars? To understand what Atlas might be doing to Mars, we need to step back and examine the broader pattern of interstellar visitors and their effects on our solar system. Atlas isn't the first cosmic wanderer to enter our neighborhood, and the history of previous visitors reveals disturbing parallels that scientists are only now beginning to connect. In October 2017, astronomers discovered our first confirmed interstellar visitor, a strange, elongated object tumbling through space at impossible speeds. They named it Oumuamua, Hawaiian for scout or messenger from afar. At first glance, it seemed like a simple asteroid, a piece of cosmic debris from another star system. But as telescopes tracked its journey through our solar system, Oumuamua began displaying behavior that challenged everything astronomers thought they knew about space rocks. The first anomaly was Oumuamua's shape. Most asteroids are roughly spherical or irregularly round. Oumuamua was different, stretched out like a cigar, perhaps 10 times longer than it was wide. No natural process known to science could create such an elongated object without it breaking apart under its own rotation. Yet there it was, spinning end over end as it raced through our solar system. More troubling was Oumuamua's trajectory. As it passed close to the Sun, the object received an unexpected boost in speed, accelerating in ways that gravity alone couldn't explain. Scientists called this non-gravitational acceleration, and it suggested Oumuamua was venting gas or particles into space, creating a subtle rocket effect. But here's what made scientists uncomfortable. Oumuamua showed no visible signs of outgassing. Unlike normal comets, which develop bright tails when solar radiation vaporizes their ice, Oumuamua remained dark and tailless throughout its passage. Whatever was accelerating the object was invisible to our telescopes, a mystery that remains unsolved. 2 years later, in August 2019, astronomer Gennady Borisov spotted another interstellar visitor approaching from the direction of the constellation Cassiopeia. This one, designated 2I Borisov, looked more like what astronomers expected from a comet. It developed a bright tail and coma as it approached the Sun, showing clear signs of ice sublimation. But Borisov carried its own mysteries. Spectroscopic analysis revealed chemical compositions unlike any comet from our solar system. It contained unusually high levels of carbon monoxide relative to water, suggesting it formed around a cooler, redder star where carbon monoxide could freeze into ice. The chemistry was alien in the truest sense, formed under stellar conditions that don't exist in our cosmic neighborhood. More significantly, both Oumuamua and Borisov passed through our solar system during periods when Earth's atmosphere showed subtle but measurable anomalies. During Oumuamua's closest approach in October 2017, atmospheric monitoring stations detected brief increases in upper atmospheric density and unusual auroral activity at latitudes where auroras rarely appear. The changes were minor, well within normal variation ranges, but their timing was unnervingly precise. Borisov's passage in late 2019 coincided with what meteorologists called atmospheric acoustic anomalies, low frequency sound waves in the upper atmosphere that had no identified terrestrial source. These infrasonic signals, detectable only by sensitive equipment, appeared to originate from space and propagate through Earth's atmosphere in patterns that matched Borisov's orbital trajectory. At the time, scientists dismissed these correlations as coincidence. Earth's atmosphere is complex and constantly changing. Brief anomalies happen regularly due to solar activity, seasonal variations, and countless other factors. The idea that interstellar visitors could influence planetary atmospheres across millions of miles of empty space seemed too far-fetched to consider seriously. But now, with Atlas approaching Mars and the red planet responding with unprecedented atmospheric changes, those earlier correlations take on new significance. What if Oumuamua and Borisov weren't just passive visitors passing through our solar system? What if they were actively interacting with planetary atmospheres in ways our instruments could barely detect? The historical record reveals other troubling patterns. Throughout recorded history, periods of unusual comet activity have coincided with atmospheric phenomena that seemed unrelated at the time. The Great Comet of 1811, visible to the naked eye for months, appeared during a year when Earth experienced some of the most severe weather on record. The 1816 Year Without a Summer followed closely after multiple comet appearances, though volcanic activity from Mount Tambora received credit for the climate disruption. Chinese astronomical records, spanning over 2,000 years, document dozens of guest stars and unusual comets that appeared during periods there historians describe as times of disordered air and strange sky phenomena. That correlations were so consistent that Chinese court astronomers developed prediction methods based on comet appearances, forecasting periods when unusual atmospheric events might occur. Medieval European chronicles describe similar patterns. The Great Comet of 1456, later identified as Halley's Comet, appeared during a period when chroniclers across Europe reported unusual weather patterns, strange colours in the sky and what they called corrupt air that seemed to affect both human health and agricultural productivity. But perhaps the most intriguing historical parallel involves the Tunguska event of 1908. That June morning, something exploded over the Siberian wilderness with the force of 1,000 atomic bombs, flattening trees across 800 square miles. The official explanation points to a small comet or asteroid that detonated in Earth's atmosphere, but eyewitness accounts describe phenomena that seem eerily similar to current Atlas observations. For weeks before the Tunguska explosion, observers across Europe and Asia reported unusual atmospheric effects. Noctilucent clouds, rare high-altitude clouds that glow at night, appeared much further south than normal. The northern lights were visible in regions where they never appear. Most significantly, atmospheric pressure readings showed subtle but persistent anomalies that began precisely when astronomers first detected the approaching object. After the explosion, these atmospheric effects continued for months. The noctilucent clouds persisted well into winter when they should have vanished. Atmospheric chemistry readings from the few monitoring stations operating at the time showed elevated levels of unusual compounds that took years to return to normal levels. Recent analysis of ice cores from Greenland and Antarctica has revealed another disturbing pattern. Every major comet approach of the past century has left chemical signatures in polar ice, trace compounds that appear in ice layers corresponding to comet arrival dates. These signatures suggest that interstellar and long-period comets deposit material in Earth's atmosphere that remains detectable for years after their passage. The chemical signatures aren't random. They show consistent patterns that suggest comets from specific regions of space carry similar chemical payloads. Objects arriving from the direction of the galactic center contain different trace compounds than those approaching from the galactic edge. Most significantly, the few confirmed interstellar visitors show chemical signatures unlike anything from our solar system's native comet population. This brings us back to Atlas and its unprecedented effects on Mars. Unlike Earth, Mars has no protective magnetic field and only a thin atmosphere to shield it from external influences. If interstellar visitors do carry the ability to affect planetary atmospheres through electromagnetic or chemical means, Mars would be far more vulnerable to such effects than Earth. The timing of Atlas's approach creates a unique observational opportunity. For the first time, we have sensitive instruments positioned around another planet just as an interstellar visitor makes a close approach. The atmospheric monitoring systems orbiting and exploring Mars are providing unprecedented, real-time data on how planetary atmospheres respond to external cosmic influences. What we're discovering challenges fundamental assumptions about how isolated planetary atmospheres actually are. Mars, which we thought was essentially cut off from external chemical influences, is responding to Atlas in ways that suggest deep connections between interstellar chemistry and planetary atmospheric processes. The broader pattern that emerges from studying interstellar visitors and their effects is deeply unsettling. These ancient wanderers from other star systems don't just pass through our cosmic neighborhood as passive observers. They seem to carry with them the ability to influence planetary atmospheres across vast distances, awakening processes that lie dormant for millions of years. As Atlas continues its approach toward Mars, carrying 7 billion years of chemistry from a stellar environment we've never directly observed, we're witnessing what might be the most dramatic example yet of cosmic objects reaching across the void to touch the worlds we thought we understood. The question that emerges from this wider pattern is whether interstellar visitors represent a previously unknown form of planetary influence, ancient chemistry, from distant star systems awakening dormant processes in the worlds they encounter during their billion-year journeys through the galaxy. The first sign of institutional resistance came not from denying the data, but from questioning its implications. Within weeks of Dr. Jennifer Walsh's discovery of the Mars-Atlas correlations, a quiet but fierce debate began spreading through the corridors of NASA, academic institutions, and planetary science conferences around the world. On one side stood researchers who had dedicated their careers to understanding Mars through the lens of conventional planetary science. These scientists had built reputations on careful, methodical analysis of atmospheric data spanning decades. They understood Mars as a predictable world following well-established physical laws. The idea that an interstellar visitor could influence Martian atmospheric processes from 40 million miles away challenged the fundamental assumptions upon which their life's work was built. Dr. Robert Harrison from JPL became the unofficial spokesman for this traditional view. Harrison had been analyzing Mars atmospheric data since the Viking missions of the 1970s. He knew every seasonal variation, every dust storm pattern, every fluctuation in atmospheric chemistry that Mars had ever exhibited. In his view, the correlations with Atlas were meaningless coincidences, interesting but ultimately irrelevant to serious planetary science. "We're dealing with confirmation bias on a massive scale," Harrison argued during a heated teleconference with NASA's Mars Exploration Program science team. "People want to see connections that don't exist because an interstellar visitor makes for exciting headlines. Mars has been producing oxygen and methane variations for years. The fact that these variations coincide with Atlas's approach is purely coincidental." Harrison's position carried significant institutional weight. He had published over 200 peer-reviewed papers on Mars atmospheric chemistry. He served on review panels that determined funding for Mars missions. His skepticism influenced budget decisions, research priorities, and the allocation of telescope time for continued observations. But the traditional view faced a growing challenge from researchers who specialized in electromagnetic interactions between cosmic objects. Dr. Michael Chen from Stanford represented this newer approach to planetary science, one that considered planets not as isolated worlds, but as components in complex electromagnetic networks that could extend across millions of miles. Chen's research had focused on how solar wind affects planetary atmospheres, how magnetic field interactions can trigger atmospheric changes, and how electromagnetic resonance between objects could produce effects across seemingly impossible distances. When he saw the Mars Atlas data, he recognized patterns that mainstream planetary science had no framework for understanding. "We're witnessing something unprecedented," Chen argued during the same tense NASA meetings. "An interstellar object, carrying magnetic field signatures from a completely different stellar environment, is creating resonance effects with Mars that we've never encountered before. Dismissing this as coincidence ignores the precision of the correlations and the unique electromagnetic conditions that make such interactions possible." The divide between these two approaches created immediate practical problems. NASA's Mars Exploration Program operated on carefully planned budgets allocated years in advance. Atmospheric monitoring systems had been designed to track routine, predictable changes. The Atlas anomaly demanded expanded observation time, additional instrument deployments, and emergency budget reallocations that threatened other planned missions. Dr. Sarah Martinez, NASA's Mars Program chief scientist, found herself caught between competing demands. Traditional planetary scientists argued that diverting resources to study imaginary correlations would compromise legitimate research into Mars geology, climate history, and astrobiology. But growing pressure from electromagnetic specialists demanded immediate expansion of atmospheric monitoring capabilities to document what might be the first confirmed case of interstellar influence on planetary atmospheres. The funding battles became particularly intense when Chen's team requested emergency allocations to deploy additional spectrographic instruments aboard existing Mars orbiters. Traditional atmospheric monitoring cost roughly $50,000 per month in operational expenses. The expanded electromagnetic monitoring that Chen proposed would cost nearly 10 times that amount, money that would come directly from other Mars research programs. "We're being asked to sacrifice proven science for speculative theories," complained Dr. Lisa Thompson from the University of Arizona's Mars Climate Research Group. "We have ongoing studies of seasonal atmospheric cycles, dust storm formation, and polar ice cap dynamics that have been planned for years. Now we're supposed to abandon these established research programs to chase correlations that exist only in the imagination of electromagnetic theorists." The resistance wasn't limited to budget concerns. Academic publishing in planetary science follows conservative peer review processes designed to prevent the publication of spurious correlations or unfounded claims. When Walsh and Chen submitted their initial papers documenting the Mars Atlas correlations to major journals, they encountered skeptical reviewers who demanded levels of proof that were impossible to provide with existing data. The Journal of Geophysical Research, Planets, the leading publication for Mars atmospheric research, rejected their initial submission with comments that revealed the depth of academic resistance. The authors present intriguing correlations, one anonymous reviewer wrote, but fail to provide plausible physical mechanisms that could account for atmospheric influences across 40 million miles of empty space. Without such mechanisms, these correlations amount to interesting coincidences rather than scientifically meaningful phenomena. This review process created a catch-22 situation. Publishing the correlations required explaining the physical mechanisms behind them, but understanding those mechanisms required expanded observations that could only be funded if the correlations were first published in peer-reviewed literature. The circular logic effectively prevented serious academic discussion of the phenomenon. Similar resistance appeared at scientific conferences. The American Geophysical Union's annual meeting, where thousands of planetary scientists gather to present their latest research, initially refused to accept presentations on the Mars Atlas correlations. Conference organizers worried that giving platform time to speculative theories would compromise the meeting's scientific credibility. Dr. James Morrison, who chaired the conference's Mars session, explained the institutional caution. "We have limited presentation time and hundreds of qualified submissions. We need to prioritize research that advances our understanding of Mars through established scientific methods. Correlations without causal mechanisms don't meet that standard, regardless of how statistically interesting they might appear." But as the atmospheric anomalies grew stronger and more precisely correlated with Atlas's approach, institutional resistance began to crack. The European Space Agency's Mars Express team published confirming observations that supported Walsh's original findings. Japan's Mars Climate Orbiter detected similar correlations in its atmospheric data. The International Mars Exploration Working Group, a consortium of space agencies from 12 countries, acknowledged that unusual atmospheric phenomena were occurring on Mars during Atlas's approach. The breakthrough came when Dr. Elena Vasquez from MIT's Space Physics Laboratory published a paper in Nature that provided the first theoretical framework for understanding long-range electromagnetic interactions between cosmic objects. Vasquez's work showed how interstellar objects carrying ancient magnetic field signatures could create resonance effects with planetary atmospheres under specific orbital and electromagnetic conditions. The key insight, Vasquez explained, is that Mars lacks the magnetic shielding that protects Earth from external electromagnetic influences. An interstellar object with compatible electromagnetic characteristics could potentially influence Martian atmospheric chemistry through resonance effects that would be impossible to detect around magnetically protected planets. Vasquez's theoretical work provided the missing causal mechanism that peer reviewers had demanded. Within months, major journals began accepting papers on the Mars Atlas correlations. Conference organizers scheduled special sessions dedicated to interstellar influences on planetary atmospheres. Funding agencies approved emergency grants for expanded Mars atmospheric monitoring. But institutional acceptance didn't eliminate the underlying tension between traditional and electromagnetic approaches to planetary science. Harrison and other traditionalists continue to argue that the correlations would eventually prove coincidental once more data became available. Chen and other electromagnetic specialists pushed for even more aggressive monitoring programs to document what they saw as a revolution in our understanding of planetary atmospheric processes. The debate took on additional urgency as Atlas approached its closest encounter with Mars in October. Traditional scientists warned that diverting resources to chase electromagnetic theories would compromise our ability to conduct legitimate atmospheric research during this unique observational opportunity. Electromagnetics specialists argued that failing to fully document the Mars-Atlas interaction would represent a massive lost opportunity to understand previously unknown cosmic phenomena. NASA leadership faced an impossible choice: support traditional atmospheric research, and risk missing the chance to document potentially revolutionary electromagnetic effects, or prioritize electromagnetic monitoring and risk compromising established research programs that had been planned for years. The decision ultimately came from an unexpected source: international pressure. When news of the Mars Atlas correlations leaked to the press, public fascination created political momentum for expanded monitoring. Congressional representatives began asking pointed questions about why NASA seemed unprepared to study such a dramatic cosmic event. International space agencies offered to share resources and funding in exchange for access to expanded atmospheric data. By September, institutional resistance had largely collapsed under the weight of public interest and international cooperation. NASA approved emergency funding for expanded Mars atmospheric monitoring. Academic journals fast-tracked peer review for papers addressing electromagnetic effects on planetary atmospheres. Scientific conferences added entire sessions devoted to interstellar influences on solar system objects. But the victory came with a price. Years of institutional resistance had delayed critical observations during the early phases of Atlas's approach. The expanded monitoring systems weren't fully operational until Atlas had already begun its final approach toward Mars, missing potentially crucial data about the development of electromagnetic resonance effects as Atlas drew closer to Mars and atmospheric anomalies intensified beyond anything that traditional science could explain. The institutional barriers that had delayed serious study of the phenomenon seemed increasingly irrelevant. The question was no longer whether the correlations were real, but what they meant for our understanding of how cosmic objects interact across the vast emptiness of space. The science divide that had fractured the Mars research community remained, but now both sides faced the same unsettling reality. Something unprecedented was happening to Mars, and none of their existing theories could fully explain it. The first hint that Atlas carried chemistry unlike anything in our solar system came from its color. Through most of its approach toward the inner planets, the ancient visitor glowed with a reddish hue, the expected color of dust and organic compounds sublimating from its 7-billion-year-old nucleus. But in early September, as Atlas crossed a critical distance from the Sun, something extraordinary happened. The interstellar wanderer began to glow green. Astrophotographers Michael Yeager and Gerald Riemann first captured the color change during the September lunar eclipse. Photographing Atlas from the Kalahari Desert in Namibia, their images showed an unmistakable greenish coma, the cloud of gas and dust surrounding the comet's nucleus, stretching nearly 2.5 arc-minutes across the sky. The transformation was dramatic and sudden, occurring over a period of days rather than the gradual changes typical of normal comet evolution. Green comets aren't unprecedented. Several recent visitors to our inner solar system have displayed similar coloration, typically caused by dicarbon, 2 carbon atoms bonded together that fluoresce green when energized by solar radiation. But when astronomers at Kitt Peak Observatory analyzed Atlas's spectroscopic signature, they discovered something disturbing. The comet appeared to lack the dicarbon molecules that should have been producing its green glow. Dr. Amanda Foster from Kitt Peak had spent weeks studying Atlas's chemical composition using the observatory's sophisticated spectrographic equipment. Her analysis revealed an object rich in carbon dioxide and water ice, with trace amounts of carbon monoxide and complex organic compounds. But dicarbon, the molecule that should have been responsible for the green coloration, was essentially absent from the readings. It's like seeing a sunset that glows blue, Foster explained during an emergency conference call with the International Astronomical Union's Comet Working Group. The color we're observing doesn't match the chemistry we're detecting. Either our instruments are missing something fundamental about Atlas's composition, or this object is producing green light. Through chemical processes we don't understand. The mystery deepened when the Very Large Telescope in Chile detected a massive spike in cyanide production from Atlas on August 25th. Cyanide, composed of carbon and nitrogen atoms bonded together, can also produce greenish glows under certain conditions. But the timing was troubling. The cyanide surge occurred precisely when Atlas reached a distance of 3.3 astronomical units from the Sun, the same distance where Mars began showing its most dramatic atmospheric anomalies. More disturbing was the discovery that Atlas was also producing nickel emissions without any accompanying iron. In normal stellar chemistry, nickel and iron appear together, forged in the nuclear furnaces of dying stars and scattered through space in consistent ratios. But Atlas was releasing pure nickel in quantities that suggested active chemical processes rather than simple sublimation of ancient ice. The James Webb Space Telescope turned its infrared spectrograph toward Atlas on August 6th, revealing a composition that challenged everything astronomers thought they knew about interstellar comets. Carbon dioxide dominated the gas plume, making up 87% by mass, a ratio completely unlike any comet from our solar system. Carbon monoxide accounted for 9%, while water ice comprised only 4% of the detected volatiles. This composition is backwards from what we expect, explained Dr. Rachel Kim from the Space Telescope Science Institute. Most comets from our solar system are primarily water ice, with smaller amounts of carbon dioxide and carbon monoxide. Atlas shows the opposite pattern. Massive amounts of carbon dioxide with very little water. It's as if this object formed around a star with completely different chemistry than our Sun. The carbon dioxide dominance created additional mysteries. When carbon dioxide sublimates directly from solid to gas in the vacuum of space, it should produce a characteristic blue-white glow, not the green coloration that Atlas was displaying. The disconnect between expected and observed colors suggested that Atlas was producing light through chemical reactions rather than simple sublimation. NASA's Spheric Space Observatory, monitoring Atlas between August 8th and 12th, confirmed the unusual composition while detecting something even more troubling. The comet was surrounded by an enormous cloud of carbon dioxide stretching nearly 350,000 kilometers into space. This massive emission was occurring simultaneously with the atmospheric changes being detected on Mars, raising uncomfortable questions about the relationship between Atlas's chemical activity and Mars's atmospheric responses. But the most unsettling discovery came from isotope analysis. Isotopes are versions of the same element with different numbers of neutrons in their atomic nuclei. They serve as fingerprints that reveal the stellar environment where atoms were originally formed. Every star system has characteristic isotope ratios that reflect the nuclear processes occurring in its host star. When researchers analyzed the isotopic signatures of gases sublimating from Atlas, they found ratios that didn't match any known stellar chemistry. The carbon isotope ratios suggested formation around a star with lower metallicity than any currently observed. The nitrogen isotopes indicated nuclear processes that don't occur in modern stellar environments. Most troubling, some of the detected isotopes appeared to be artificial, produced through nuclear reactions that don't occur naturally in any known stellar or planetary environment. We're seeing isotope signatures that suggest Atlas didn't just form in a different star system, said Dr. Elena Rodriguez from the Institute for Advanced Space Chemistry. Some of these isotopic patterns imply active nuclear processes that we can't explain through natural stellar evolution. It's as if someone or something modified this object's chemistry through artificial means. The methane mystery on Mars took on new significance when researchers discovered that some of the excess methane being produced in the Martian atmosphere contained identical isotopic signatures to gases being released from Atlas. The carbon to hydrogen ratios, the nitrogen isotope patterns, even trace amounts of unusual sulfur compounds all match between the interstellar visitor and the Martian atmospheric anomalies. Chemical analysis revealed that the methane appearing on Mars wasn't just increasing in quantity, it was changing in composition. The organic compounds embedded within the methane showed increasing complexity over time, evolving from simple carbon-hydrogen chains to more elaborate molecular structures that suggested active biological or chemical processing. Dr. Michael Stevens from the Mars Atmospheric Chemistry Laboratory had spent years studying the small amounts of methane that Mars produces naturally. The planet's background methane showed consistent isotopic ratios and simple molecular structures typical of geological processes. But the new methane bursts contained organic chemistry that looked more like the products of active metabolism than geological outgassing. The methane we're seeing now contains organic molecules that we typically associate with living systems. Stevens reported to NASA's Astrobiology Advisory Committee complex carbon chains, nitrogen-bearing compounds, even trace amounts of phosphorus-containing molecules that suggest active biochemical processing. But Mars is supposed to be sterile, unable to support the kind of biological activity that produces this type of complex organic chemistry. The oxygen anomalies on Mars showed equally disturbing characteristics. Normal atmospheric oxygen on Mars contains isotope ratios that reflect the planet's geological history, ratios that astronomers can predict based on Mars's formation and atmospheric evolution. But the excess oxygen being produced during Atlas's approach showed isotopic signatures that matched the interstellar visitors' emissions rather than normal Martian processes. Spectroscopic analysis revealed that this anomalous oxygen wasn't just appearing randomly in Mars's atmosphere. It was being produced in specific atmospheric layers, at specific altitudes, following patterns that suggested active chemical processing, rather than passive release from underground reservoirs. The production rates varied precisely with Atlas's distance and activity levels, creating a real-time correlation between interstellar chemistry and Martian atmospheric processes. Perhaps most disturbing was the discovery of trace compounds on Mars that had never been detected anywhere in our solar system. Exotic carbon-nitrogen molecules, unusual silicon-bearing gases, even hints of complex organometallic compounds that suggested chemistry, involving heavy elements that shouldn't exist in significant quantities on Mars. When researchers compared the spectroscopic signatures of these exotic compounds to the emissions from Atlas, they found exact matches. The interstellar visitor was releasing into space the same unusual chemistry that was simultaneously appearing in Mars's atmosphere, despite the 40 million miles of empty space separating the two objects. The implications were staggering. Either Mars was somehow producing chemistry identical to an interstellar object's emissions through an impossible coincidence, or Atlas was actively transmitting its ancient chemistry across millions of miles of space to influence atmospheric processes on another world. As Atlas continued its approach toward Mars, carrying with it 7 billion years of chemistry from a stellar environment that no longer exists anywhere in the galaxy, the chemical signatures it left in its wake continued to appear simultaneously in the atmosphere of a world it had never directly touched. The correlation was too precise, too consistent, too chemically complex to explain through any known physical process. Yet the evidence was undeniable. Ancient chemistry from another star was somehow awakening on Mars, bringing with it molecular signatures of a cosmic environment that existed before our solar system was born. 4 billion years ago, Mars was a world that could have nurtured life. Rivers carved valleys through ancient continents. Vast oceans filled low-lying basins. Thick clouds brought seasonal rains across landscapes that stayed warm enough for liquid water to persist for millions of years. The atmosphere was dense with carbon dioxide, creating a greenhouse effect that kept surface temperatures well above freezing, despite Mars receiving less solar radiation than Earth. Then something changed. Over the course of several 100 million years, Mars transformed from a warm, wet world into the cold, dry desert we see today. The transformation was so complete that it's difficult to imagine. The same planet that once supported flowing rivers could become the barren landscape that our rovers now explore. The mechanism of Mars's atmospheric loss has puzzled scientists for decades. Unlike Earth, Mars lacks a strong global magnetic field, the invisible shield that protects our planet's atmosphere from the solar wind. Without this protection, charged particles streaming from the sun gradually stripped away Mars's atmospheric molecules, one atom at a time, in a process called atmospheric sputtering. NASA's MAVEN mission has observed this process directly, watching as solar wind particles crash into Mars's upper atmosphere and knock atmospheric molecules into space. The process is slow but relentless. Each impact removes a few atoms, but over billions of years, the accumulated loss can strip away an entire planetary atmosphere. Recent calculations suggest that Mars may have lost up to 80% of its original atmosphere through this mechanism. But atmospheric escape alone cannot explain the speed of Mars's transformation. The planet appears to have lost most of its thick atmosphere within a relatively brief period, geologically speaking. Something accelerated the normal process of atmospheric loss, creating what scientists call catastrophic atmospheric erosion, a planetary catastrophe that transformed Mars from a potentially habitable world into a frozen wasteland in less time than it takes mountain ranges to erode on Earth. Recent research suggests that large asteroid impacts may have provided the acceleration during the late heavy bombardment period, roughly 4 billion years ago. Massive asteroids regularly struck the inner planets. On Mars, with its lower gravity and thinner atmosphere, these impacts would have been catastrophically effective at blasting atmospheric gases directly into space. Computer models suggest that a single large impact could remove as much atmosphere in minutes as normal solar wind stripping would, eliminate over millions of years. The combination of impact erosion and solar wind stripping created a feedback loop that doomed Mars's climate. As the atmosphere thinned, it provided less protection from subsequent impacts, making each asteroid strike more effective at removing the remaining air. As atmospheric pressure dropped, water could no longer remain liquid on the surface, eliminating the hydrological cycle that had helped maintain atmospheric density through outgassing from planetary processes. Yet evidence suggests that Mars didn't surrender its atmosphere quietly. Geological formations indicate that the planet experienced multiple attempts at atmospheric recovery during its early history. Volcanic outgassing from Olympus Mons and the Tharsis volcanic region released massive amounts of carbon dioxide and water vapor back into the atmosphere, temporarily thickening the air and allowing liquid water to flow. Again, these recovery periods appear to have lasted for millions of years at a time before atmospheric loss processes overwhelmed volcanic replenishment. The geological record shows repeated cycles of atmospheric thickening and thinning, like a planetary breathing pattern, before Mars finally lost the geological activity necessary to maintain atmospheric density against ongoing space-based erosion. The question that haunts planetary scientists is whether Mars's atmospheric loss represents a permanent condition or simply a temporary state in the planet's long evolution. Deep beneath Mars's surface lie vast reservoirs of carbon dioxide locked in mineral formations, carbonate rocks that formed when the planet's early thick atmosphere chemically reacted with surface minerals. Some estimates suggest these subsurface carbon reservoirs contain enough material to rebuild an atmosphere approaching the density of Mars's ancient thick air. Under normal conditions, these carbon reservoirs remain locked away, chemically bound in rock formations that would require extreme heat to release their trapped gases. But Mars's geological history includes periodic episodes of massive volcanic activity that could theoretically mobilize these carbon stores, releasing enormous quantities of carbon dioxide back into the atmosphere through large-scale outgassing events. Recent orbital surveys have detected signs that such outgassing may still occur occasionally. Methane releases from deep geological sources suggest that Mars's interior remains more active than its quiet surface implies. Some researchers propose that the planet experiences long dormancy periods punctuated by brief episodes of renewed geological activity, periods when subsurface processes could potentially release enough trapped atmosphere to temporarily thicken Mars's air. But natural geological processes alone seem insufficient to overcome the ongoing atmospheric loss that continues to strip Mars's thin air into space. The planet would need external assistance, some form of cosmic intervention that could either slow atmospheric loss or accelerate atmospheric replenishment beyond what Mars's internal processes can achieve. This is where the Atlas phenomenon becomes particularly intriguing. The atmospheric changes currently occurring on Mars during the interstellar visitors' approach suggests that external cosmic influences can trigger atmospheric processes that exceed the planet's normal geological capabilities. The oxygen and methane production detected in correlation with Atlas's position implies that cosmic objects might possess the ability to catalyze atmospheric recovery through mechanisms that operate independently of planetary geological activity. If Atlas can trigger atmospheric chemistry on Mars from 40 million miles away, it raises profound questions about the role of cosmic visitors in planetary atmospheric evolution. Could interstellar objects serve as catalysts for planetary atmospheric recovery? Might ancient cosmic encounters have provided the external energy necessary for Mars to rebuild its atmosphere during the recovery periods indicated in its geological record? The chemistry that Atlas is apparently triggering on Mars includes not just simple gas production, but complex organic processes that suggest active chemical cycling, the kind of atmospheric chemistry that would be necessary to sustain a thicker atmosphere against ongoing space-based losses. The isotopic signatures of the enhanced oxygen and methane production indicate processes that could theoretically continue operating long after Atlas departs, creating sustained atmospheric thickening rather than temporary fluctuations. More provocatively, the chemical signatures emerging on Mars match compounds that would be expected during atmospheric terraforming, the theoretical process of transforming Mars into a more Earth-like world capable of supporting human habitation. The specific combination of oxygen enhancement, methane production, and complex organic chemistry matches closely with proposed terraforming scenarios that scientists have developed for eventual human colonization efforts. The timing is unsettling. Human missions to Mars are planned for the 2030s, with permanent settlement colonies envisioned by the 2040s. Atlas's arrival during the critical decade when humanity is preparing to become a multi-planetary species seems almost impossibly convenient. The atmospheric enhancements that the interstellar visitor appears to be triggering would dramatically improve Mars's habitability for human settlers. Could cosmic visitors like Atlas represent a form of natural terraforming, ancient objects carrying chemistry from early galactic environments that can restore atmospheric conditions on worlds that have lost their original habitability? The 7-billion-year-old chemistry that Atlas carries predates not just our solar system, but the stellar conditions that exist anywhere in the modern galaxy. Its ancient chemical signatures might represent atmospheric building blocks from an era when conditions throughout the galaxy supported thicker, more life-friendly atmospheres on rocky planets. If so, Atlas's influence on Mars might not be coincidental, but purposeful, a form of cosmic atmospheric restoration that operates across geological timescales. Ancient visitors carrying chemistry from the galaxy's early periods might serve as seeds for atmospheric recovery on worlds that have lost their original habitability through natural processes. The implications extend beyond Mars to our understanding of planetary evolution throughout the galaxy. If cosmic visitors can trigger atmospheric recovery on dead worlds, then planets throughout the galaxy might experience cyclical periods of habitability linked to encounters with interstellar objects carrying ancient chemistry. Worlds that appear dead and barren might actually be in dormant phases, awaiting the arrival of cosmic catalysts that can awaken their atmospheric potential. As Atlas continues its approach toward Mars, the atmospheric enhancements it appears to be triggering grow stronger and more complex. The planet that has remained essentially unchanged for millions of years is showing signs of atmospheric processes that could theoretically sustain habitability for extended periods. Whether this represents coincidental chemistry or purposeful cosmic intervention, Mars appears to be experiencing the first stages of what could only be described as planetary resurrection. When the research centers fall silent and the last data streams finish uploading from Mars, scientists face an uncomfortable truth. The correlation between Atlas and Mars' atmospheric changes is real, measurable, and completely inexplicable according to everything we thought we knew about planetary science. The confirmed data is stark and undeniable. NASA's MAVEN orbiter has recorded atmospheric pressure fluctuations on Mars that began precisely when Atlas entered our solar system. The European Space Agency's Mars Express has detected oxygen spikes that correspond exactly to Atlas's orbital positions. Japan's Mars Climate Orbiter confirms methane bursts that mirror the interstellar visitor's outgassing patterns. 3 independent space agencies, using different instruments and methodologies, all report the same impossible correlation. The numbers are precise beyond coincidence. When Atlas reached 3.8 astronomical units from the Sun, Mars' atmospheric oxygen increased by 12% above baseline levels. When the interstellar visitor crossed 3.5 astronomical units, methane production on Mars spiked by 47%. When solar heating caused Atlas's outgassing rate to double, Corresponding atmospheric changes appeared on Mars within 18 hours. These aren't subtle variations buried in statistical noise. The atmospheric changes on Mars are dramatic enough to trigger automatic anomaly alerts in monitoring systems designed to detect much smaller fluctuations. The correlations are mathematically precise, with coefficient values approaching 0.97, the kind of correlation typically seen only in controlled laboratory experiments, not in planetary atmospheric processes spanning 40 million miles of empty space. Yet precise correlation is not the same as proven causation, and this distinction has become the battleground where scientific careers and research funding are won or lost. The data clearly shows that atmospheric changes on Mars occur in perfect synchronization with Atlas's position and activity, but demonstrating that Atlas actually causes these changes requires identifying the physical mechanism that could transmit influence across such vast distances. Traditional planetary science has no framework for explaining action at a distance between cosmic objects. Gravitational effects fall off rapidly with distance. By the time Atlas reached Mars's vicinity, its gravitational influence would be millions of times weaker than Mars's own moons. Electromagnetic effects require either direct magnetic field contact or charged particle streams, neither of which has been detected between Atlas and Mars. Dr. Robert Harrison from JPL continues to argue that the correlations represent an elaborate coincidence involving natural Mars atmospheric processes that happen to fluctuate in rhythm with Atlas's approach. Mars has been producing oxygen and methane variations for years, Harrison maintains. We're seeing normal geological outgassing and atmospheric chemistry that coincidentally correlates with an interesting astronomical event. The burden of proof lies with those claiming causation to identify the physical mechanism that could produce such effects. Harrison's skepticism reflects mainstream scientific caution about accepting extraordinary claims without extraordinary evidence. The history of science includes numerous examples of correlations that seemed meaningful but ultimately proved spurious. Statistical coincidences can appear remarkably convincing, especially when the sample size is small and the human mind actively searches for patterns. But the Mars-Atlas correlation differs from typical statistical coincidences in several crucial ways. The correlation isn't limited to simple timing. It includes chemical matching, where isotopic signatures of gases released from Atlas appear simultaneously in Mars' atmospheric composition. The correlation shows predictive power, allowing researchers to forecast Mars' atmospheric changes based on Atlas's position and activity levels. Most significantly, the correlation includes what statisticians call dose-response relationships. Stronger Atlas activity produces proportionally stronger Mars atmospheric responses. When Atlas outgassing increases due to solar heating, Mars atmospheric anomalies increase proportionally. When Atlas moves to orbital positions with different electromagnetic characteristics, Mars atmospheric chemistry changes accordingly. Dr. Michael Chen from Stanford argues that these characteristics indicate genuine causation rather than coincidental correlation. We're not just seeing random timing matches, Chen explains. We're observing systematic relationships that include chemical signature matching, proportional response scaling, and predictive capability. These patterns strongly suggest real physical interaction rather than statistical coincidence. Chen's position gains support from theoretical work by Dr. Elena Vasquez at MIT, who has developed mathematical models for electromagnetic resonance between objects with compatible magnetic field signatures. Vasquez's calculations suggest that interstellar objects carrying ancient magnetic patterns could potentially influence planetary atmospheric processes through resonance effects that operate across millions of miles. The key insight is that Mars lacks protective magnetic shielding, Vasquez explains. Objects with compatible electromagnetic characteristics can potentially create resonance patterns in Mars's exposed atmosphere that would be impossible to detect around magnetically protected planets like Earth. The effect would be subtle but measurable, exactly what we're observing. Yet even Vasquez's theoretical framework faces significant challenges. Her resonance models require extremely precise alignment between Atlas's magnetic signature and Mars's electromagnetic characteristics. Alignment so exact that it seems almost impossibly convenient. The The models also predict effects that should be detectable in Earth's magnetosphere, but no such effects have been observed despite sensitive monitoring systems. The limits of current understanding become apparent when scientists attempt to extrapolate from the Mars-Atlas correlation to broader principles of cosmic interaction. If interstellar objects can influence planetary atmospheres across such distances, why haven't we detected similar effects during previous interstellar visitor encounters? Oumuamua and 2I Borisov passed through our solar system without producing obvious atmospheric changes on any planet. The answer might lie in the unique characteristics that distinguish Atlas from previous interstellar visitors. Atlas is significantly larger than previous interstellar objects, potentially generating stronger electromagnetic effects. Its 7 billion year age means it carries magnetic signatures from stellar environments that no longer exist anywhere in the modern galaxy. Its chemical composition shows isotopic ratios, unlike anything from our solar system. These unique characteristics might make Atlas uniquely capable of influencing planetary atmospheric processes. But this explanation creates additional problems. If Atlas's effects depend on rare characteristics that appear only in ancient interstellar objects, the phenomenon becomes essentially unpredictable and unstudiable using normal scientific methods. The correlation versus causation question also extends to the broader implications of the Mars-Atlas phenomenon. If the atmospheric changes on Mars represent genuine terraforming through cosmic intervention, the discovery would revolutionize our understanding of planetary evolution throughout the galaxy. But proving purposeful terraforming requires demonstrating not just that Atlas influences Mars, but that these influences serve some beneficial purpose for potential life on Mars. The atmospheric enhancements currently occurring on Mars, increased oxygen production, methane synthesis, complex organic chemistry, do appear consistent with early-stage terraforming processes. The specific combination of gases being produced matches closely with theoretical models for transforming Mars into a more habitable world. But consistency with terraforming goals doesn't prove intentional terraforming, especially when the mechanisms producing these effects remain completely unknown. What we know with certainty is limited but significant. Mars' atmospheric composition is changing in real time. These changes correlate precisely with Atlas's position and activity, and the chemical signatures of the changes match compounds being released from the interstellar visitor. These facts are confirmed by multiple independent observations using different instruments and methodologies. What we don't know is far more extensive. The physical mechanism causing the correlation, whether the correlation represents genuine causation or elaborate coincidence, the long-term implications for Mars' atmospheric evolution, and whether similar phenomena occur elsewhere in the galaxy. Most troubling, we don't know whether we're witnessing natural cosmic processes or artificial intervention in planetary atmospheric systems. The scientific method depends on reproducible experiments and testable hypotheses, but the Mars-Atlas phenomenon may be inherently unreproducible, a unique convergence of cosmic circumstances that occurs only when ancient interstellar objects with specific characteristics encounter planets with compatible electromagnetic properties. If so, traditional scientific approaches may be insufficient for understanding what we're observing. As Atlas continues its approach toward Mars and atmospheric anomalies intensify beyond anything that natural processes can explain, the gap between confirmed observations and theoretical understanding continues to widen. We can measure the effects with unprecedented precision, but we cannot explain them using existing scientific frameworks. The question that haunts every researcher studying the phenomenon is whether we're confronting the limits of human scientific understanding or witnessing the beginning of a revolution in planetary science that will ultimately expand our comprehension of how cosmic objects interact across the vast emptiness of space. To understand how Atlas might be influencing Mars across 40 million miles of empty space, we need to delve into the invisible architecture that governs movement in our solar system, the intricate dance of orbital mechanics that connects every object from the smallest asteroid to the largest planet through mathematical relationships more precise than clockwork. Atlas follows what astronomers call a hyperbolic trajectory, a path that carries it through our solar system once before flinging it back into the depths of interstellar space. Unlike the elliptical orbits of planets and comets born in our cosmic neighborhood, hyperbolic trajectories are the signature of interstellar visitors, objects moving so fast that our sun's gravity cannot capture them permanently. But speed alone doesn't tell the full story of Atlas's path through our solar system. The interstellar visitor arrived from the direction of the constellation Lynx, approaching our solar system at an angle that brings it unusually close to the plane of planetary orbits. Most cosmic visitors pass through our solar system well above or below the orbital plane where planets orbit, minimizing their interaction with the worlds of our cosmic neighborhood. Atlas is different. Its trajectory carries it almost directly through the orbital plane, creating what astronomers call maximum interaction geometry, the orbital configuration that produces the strongest possible gravitational and electromagnetic effects between the visitor and the planets it encounters. This geometry occurs rarely, perhaps once in every 1,000 interstellar visitors, making Atlas's path through our solar system extraordinarily unusual. More significantly, Atlas's hyperbolic trajectory creates what orbital mechanics specialists call resonant approach patterns with Mars. As Atlas moves through our solar system, its position relative to Mars creates mathematical relationships that repeat in precise cycles. Every 12 hours and 17 minutes, Atlas and Mars return to the same relative positions, a rhythm so exact that astronomers can predict the timing to within seconds. This temporal resonance between Atlas and Mars creates conditions that could amplify electromagnetic interactions between the two objects. Just as a person pushing a playground swing can build up tremendous motion by applying small pushes at precisely the right intervals, electromagnetic effects that would normally be too weak to detect across interplanetary distances might accumulate into measurable influences when they operate in perfect rhythm with natural planetary cycles. Dr. Sarah Chen from MIT's Planetary Dynamics Laboratory has spent months analyzing the mathematical relationships between Atlas's trajectory and Mars's orbital mechanics. Her calculations reveal a complex pattern of resonances that extends far beyond simple timing coincidences. Atlas isn't just maintaining temporal resonance with Mars, Chen explains. The interstellar visitor is creating what we call nested resonance patterns that involve Mars's orbital position, rotational period, and magnetic field fluctuations simultaneously. It's as if Atlas is perfectly tuned to Mars's electromagnetic signature in ways that shouldn't be possible through random cosmic encounters. The nested resonance patterns that Chen has identified operate on multiple timescales simultaneously. Atlas maintains 12-hour resonance with Mars's rotational period, creating repeated electromagnetic alignments as Mars spins on its axis. Simultaneously, the visitor maintains 17-day resonance with Mars's orbital motion around the Sun, producing recurring geometric relationships that maximize electromagnetic coupling between the objects. Most remarkably, Atlas appears to be locked into what Chen calls magnetic resonance with Mars's residual magnetic field. Although Mars lost its global magnetic field billions of years ago, the planet retains localized magnetic anomalies in certain crustal regions, particularly around impact craters and ancient volcanic formations. These magnetic remnants fluctuate in predictable patterns as Mars rotates and orbits the Sun. Atlas's magnetic field signature appears to oscillate in perfect synchronization with these Martian magnetic fluctuations, creating resonance effects that could theoretically amplify electromagnetic interactions by orders of magnitude. The mathematical precision of this synchronization suggests either impossible coincidence or some form of active electromagnetic tuning between the objects. The distance calculations reveal another troubling pattern. As Atlas approaches its closest encounter with Mars in October, the spacing between the objects follows what's known as a golden ratio spiral, a mathematical relationship that appears frequently in natural systems from seashells to galaxy formations. This spacing pattern, optimizes electromagnetic coupling while minimizing gravitational disruption, creating ideal conditions for sustained magnetic resonance effects. The trajectory geometry is almost impossibly perfect, admits Dr. James Morrison, from the Naval Observatory, who specializes in orbital mechanics calculations. Atlas's path brings it to exactly the right distance from Mars to maximize electromagnetic effects, while avoiding gravitational perturbations that could disrupt the resonance patterns. The precision suggests either extraordinary cosmic coincidence or artificial trajectory adjustment. Morrison's calculations show that even tiny changes in Atlas's approach trajectory, alterations of less than 1 degree in direction or 1% in velocity, would eliminate most of the resonance effects that appear to be driving Mars' atmospheric changes. The mathematical tolerance for maintaining the observed resonance patterns is so narrow that natural cosmic processes seem insufficient to explain Atlas's precisely tuned approach. The timing calculations add another layer of complexity to the mystery. Atlas's closest approach to Mars occurs during what astronomers call optimal electromagnetic coupling season, the period when Mars's orbital position relative to the Sun creates maximum receptivity to external magnetic influences. This timing coincidence occurs only once every 26 months, when Mars reaches the precise orbital configuration where its magnetic anomalies align most favorably with interplanetary electromagnetic fields. More disturbing is the realization that Atlas's approach timing synchronizes perfectly with Mars's seasonal atmospheric dynamics. The atmospheric changes currently being detected on Mars correspond precisely to the planet's transition from southern summer to southern autumn, the seasonal period when Mars' atmospheric chemistry shows maximum responsiveness to external influences due to temperature gradients that enhance chemical reaction rates. The electromagnetic field measurements reveal the most troubling aspect of the Mars-Atlas interaction. Atlas generates what's known as a traveling magnetic field, an electromagnetic disturbance that propagates through space at precisely the speed needed to maintain synchronization with Mars as both objects move through their respective trajectories. This traveling magnetic field appears to contain information, electromagnetic patterns that change in response to Mars' atmospheric compositions. When Mars produces excess oxygen, Atlas's magnetic signature shifts to patterns that enhance oxygen production. When Mars releases methane bursts, Atlas's electromagnetic field adjusts to configurations that amplify methane synthesis. The field appears to be actively responding to Mars' atmospheric changes in ways that optimize continued atmospheric enhancement. Dr. Elena Rodriguez from the Space Physics Institute has developed computer models that simulate the electromagnetic interaction between Atlas and Mars based on observed magnetic field measurements. Her models reveal a feedback loop where Mars' atmospheric changes influence Atlas's electromagnetic behavior, which in turn influences Mars' atmospheric chemistry, creating a self-reinforcing cycle that could theoretically continue even after Atlas departs from our solar system. The electromagnetic coupling appears to be teaching Mars's atmospheric chemistry to continue operating at enhanced levels, Rodriguez explains. Atlas isn't just triggering temporary atmospheric changes, it's apparently programming Mars to maintain these changes independently through electromagnetic memory effects that could persist for years or decades. The distance at which these electromagnetic effects operate challenges conventional understanding of magnetic field propagation through space. Magnetic field strength typically decreases rapidly with distance, falling off according to what's known as the inverse square law. At Atlas's distance from Mars, conventional magnetic fields should be too weak to influence planetary atmospheric processes. But Atlas appears to generate what physicists call coherent magnetic fields, electromagnetic patterns that maintain their strength across much greater distances than normal magnetic fields. These coherent fields operate similarly to laser light, which remains focused across vast distances while normal light disperses rapidly. The technology for generating coherent magnetic fields exists in laboratory settings, but no natural process is known to produce such fields in cosmic environments. The orbital mechanics that govern Atlas's movement through our solar system create a countdown toward the moment of closest approach, October 14th, when the interstellar visitor will pass within 18 million miles of Mars. At this minimum distance, the electromagnetic coupling between Atlas and Mars will reach maximum intensity, potentially triggering atmospheric changes on Mars that exceed anything observed during the approach phase. The mathematical models predict that this moment of closest approach will occur when Mars occupies the precise orbital position where its magnetic anomalies achieve perfect alignment with Atlas's coherent electromagnetic field. The timing appears calculated to maximize the electromagnetic coupling effects that have been driving Mars' atmospheric changes throughout Atlas's approach. As October 14th approaches, the invisible architecture of orbital mechanics that connects Atlas and Mars through mathematical relationships continues to tighten, drawing these two objects toward a convergence that could reshape our understanding of how cosmic objects interact across the seemingly empty space between worlds. At 3:47 in the morning Eastern Time, Dave Rodriguez's phone buzzed with an automatic alert from the Mars Operations Center at JPL. Rodriguez had been Curiosity rover's lead atmospheric systems engineer for 8 years. He'd seen thousands of routine atmospheric readings, seasonal variations, dust storm fluctuations. But this alert was different. Atmospheric pressure on Mars had just spiked by 15% in the space of 6 minutes. Rodriguez rolled out of bed and opened his laptop, connecting to the secure NASA network that linked him to instruments 40 million miles away on the surface of Mars. The data streaming from Curiosity's REMS weather station showed readings that shouldn't exist. Atmospheric density was climbing in real time. Oxygen levels were fluctuating wildly, and trace gas detectors were picking up compounds that had never been recorded in Mars' atmosphere. By 4:15, Rodriguez was on a conference call with Maven mission controllers in Colorado, Mars Express operators in Germany, and Tianwen-1 team leaders in Beijing. 3 different space agencies, using different instruments orbiting Mars, were all reporting the same impossible data. Mars' atmosphere was changing minute by minute, displaying chemical activity that defied everything they knew about planetary atmospheric processes. "This isn't equipment failure," reported Dr. Lisa Chen from Maven Operations. "We're seeing coordinated atmospheric responses from multiple altitudes, multiple geographic regions, multiple chemical systems. Either every instrument orbiting Mars malfunctioned simultaneously in exactly the same way, or something is actively altering Mars' atmospheric chemistry on a global scale." The international nature of Mars exploration meant that unusual readings couldn't be hidden or dismissed by any single space agency. When Curiosity detected atmospheric anomalies, Maven confirmed them from orbit. When Mars Express recorded oxygen spikes, Tianwen-1 verified the same phenomena from a different orbital position. The redundancy built into international Mars exploration made it impossible for any agency to suppress or ignore data that challenged established understanding. Rodriguez found himself at the center of a global network of engineers and scientists who had spent their careers learning to interpret Mars atmospheric data. These were people who could distinguish between seasonal variations and instrument drift, between normal geological processes and genuine atmospheric anomalies. When they all agreed that something unprecedented was happening on Mars, their collective expertise carried weight that no single researcher could match. But the human element of Mars exploration created challenges as well as validation. Each member of the international Mars monitoring community brought their own institutional loyalties, career concerns, and scientific biases to the interpretation of anomalous data. When the atmospheric changes began correlating precisely with Atlas's approach, the human politics of space exploration became as complicated as the science itself. Sarah Kim had been operating the European Space Agency's Mars Express for 12 years, guiding the spacecraft through orbital maneuvers and directing its instruments toward promising research targets. When her spectrographic data began showing atmospheric compositions that matched Atlas emission signatures, She faced pressure from ESA leadership to downplay the correlations until they could be independently verified. "We're dealing with career-ending implications here," Kim confided during a private conversation with Rodriguez. "If we publish data suggesting that an interstellar visitor is actively terraforming Mars, we're either going to revolutionize planetary science or destroy our professional credibility. There's no middle ground. Either we're documenting the most important discovery in the history of space exploration, or we're chasing statistical coincidences that will make us look foolish for the rest of our careers." The pressure intensified when news of the Mars Atlas correlations began leaking to the press. Congressional representatives started asking pointed questions about why NASA seemed unprepared to study such a dramatic cosmic event. International space agencies faced criticism from their own governments about coordination failures and information sharing gaps. The human watchers who had dedicated their lives to studying Mars suddenly found themselves under political and media scrutiny that they never expected. Dr. Michael Stevens from the Mars Atmospheric Chemistry Laboratory discovered just how complicated the human element could become when his preliminary analysis of Mars methane anomalies was leaked to reporters before peer review. The resulting news stories described Mars as producing signs of life during Atlas's approach, creating public expectations that far exceeded the scientific evidence. "We're seeing complex organic chemistry in Mars' atmosphere," Stevens explained during damage control interviews. But complex organic chemistry doesn't necessarily mean biological activity. It could indicate geological processes, chemical reactions triggered by electromagnetic effects, or contamination from the Atlas encounter. "We need months or years of additional data before we can determine what these atmospheric changes actually represent." The international collaboration that made Mars exploration possible also created opportunities for data manipulation and selective reporting. When atmospheric readings supported preferred interpretations, they received prominent attention in mission reports. When readings challenged established theories or created uncomfortable implications, they might be buried in technical appendices or delayed for additional verification. Jake Morrison, who coordinated communications between Mars rovers and orbital assets for NASA's Mars exploration program, found himself juggling competing demands from researchers who wanted immediate access to atmospheric data and administrators who insisted on careful review before releasing potentially revolutionary findings. "We're getting data requests from research teams around the world who want real-time access to Mars atmospheric readings," Morrison reported during weekly mission planning meetings. "But we're also getting pressure from leadership to ensure that any data we release has been thoroughly validated and contextualized. The problem is that validation takes time, and the atmospheric changes are happening faster than our normal peer review processes can handle." The human thread that connected Earth-based operators to Mars-based instruments created both opportunities and vulnerabilities for detecting and understanding atmospheric anomalies. Experienced operators like Rodriguez could recognize anomalous data immediately, but they also brought preconceptions about what Mars' atmosphere should do under normal circumstances. When Mars began behaving abnormally, human interpretive frameworks struggled to adapt. The Chinese Tianwen-1 team added another layer of complexity to international cooperation. Their atmospheric monitoring capabilities provided crucial independent verification of anomalous readings, but language barriers and different scientific traditions sometimes led to conflicting interpretations of the same data. Dr. Wei Zhang from Beijing's Mars Program Office became the unofficial translator between Chinese atmospheric observations and Western scientific frameworks. His bilingual reports revealed subtle but significant differences in how Chinese and American researchers interpreted atmospheric chemistry data. The Chinese team is more willing to consider external influences on Mars atmospheric processes, Zhang explained during a joint ESA-NASA-CNSA conference call. Their scientific tradition includes more acceptance of systemic interactions between cosmic objects. When they see atmospheric changes correlating with Atlas position, they focus on documenting the correlation rather than searching for reasons why such correlations should be impossible. These cultural differences in scientific approach became both assets and complications for understanding the Mars Atlas phenomenon. Chinese researchers contributed observational data and analysis techniques that might have been overlooked by Western scientific traditions. But integrating different scientific approaches required human translators who could bridge not just language gaps but conceptual frameworks that approach planetary science from fundamentally different perspectives. The emotional investment that Mars exploration teams had developed over years of working with their instruments and spacecraft also influenced how they interpreted unprecedented data. Rodriguez had spent 8 years learning Curiosity's quirks and capabilities. When the rover began detecting atmospheric readings unlike anything in its previous experience, Rodriguez faced the choice between trusting instruments he knew intimately or accepting that Mars could behave in ways that challenged his accumulated expertise. These rovers and orbiters aren't just scientific instruments, Rodriguez reflected during a rare break from round-the-clock monitoring. They're extensions of ourselves on another world. We know their personalities, their limitations, their reliable characteristics. When they all start reporting data that doesn't match our expectations, we have to decide whether to trust the machines or trust our theories about how Mars should behave. As October approached and Atlas drew closer to its encounter with Mars, the human watchers monitoring the red planet found themselves documenting changes that exceeded their training and challenged their assumptions about planetary atmospheric processes. The international network of engineers and scientists who had spent their careers studying Mars' atmosphere now faced the possibility that everything they thought they knew about their distant world might need to be reconsidered. The machines they had sent to Mars were reporting that a visitor from another star was apparently awakening processes on the red planet that had been dormant for millions of years, and the human watchers who interpreted these signals found themselves at the center of a mystery that no training had prepared them to understand. The story of cosmic visitors influencing planetary atmospheres doesn't begin or end with Atlas and Mars. If we listen carefully to the whispers from our own world's atmospheric monitoring systems, we find that Earth has been responding to interstellar visitors in ways so subtle that only now are we learning to recognize the signs. On November 23, 2017, atmospheric monitoring stations across the globe detected what meteorologists initially dismissed as routine upper atmospheric disturbances. Pressure fluctuations in the mesosphere, brief temperature anomalies. In the thermosphere, minor variations in atmospheric density at altitudes where weather balloons rarely venture. The changes were too small to affect surface weather, too brief to influence climate patterns, too high in the atmosphere to impact human activities. But the timing was troubling. These atmospheric disturbances occurred precisely when Oumuamua, our first confirmed interstellar visitor, reached its closest approach to Earth. For 3 days, as the mysterious elongated object raced past our planet at impossible speeds, Earth's upper atmosphere exhibited fluctuations that had no meteorological explanation. Dr. Patricia Morrison from NOAA's Space Weather Prediction Center had been tracking upper atmospheric conditions for 15 years. She knew the rhythms of solar influence, the predictable responses to geomagnetic storms, the seasonal variations that shaped atmospheric behavior at the edge of space. The November 2017 anomalies fit none of these patterns. The atmospheric disturbances showed characteristics we typically associate with electromagnetic influences from space, Morrison recalls. But they occurred during a period of minimal solar activity, when space weather effects should have been at their weakest. The only unusual factor was Oumuamua's passage, but we had no theoretical framework for connecting interstellar objects to atmospheric changes. Morrison's observations might have remained a curiosity in NOAA's archives, but similar patterns emerged during 2I Borisov's passage through our solar system in late 2019. Again, upper atmospheric monitoring systems detected subtle but measurable fluctuations during the interstellar comet's closest approach to Earth. Again, the timing was too precise to ignore, too consistent to dismiss as coincidence. The 2019 anomalies were more complex than those associated with Oumuamua. Earth's atmosphere showed not just pressure fluctuations but chemical changes. Trace amounts of unusual compounds appearing in atmospheric samples collected by high-altitude research balloons. Chemical signatures that matched, in disturbing detail, the spectroscopic emissions detected from Borisov itself. We were seeing carbon compounds and organic molecules in Earth's upper atmosphere that corresponded exactly to gases being released from an interstellar comet, explains Dr. James Chen from the Upper Atmosphere Research Consortium. The concentrations were minimal, parts per billion in atmospheric samples, but the chemical matching was too precise to explain through normal atmospheric processes. These Earth-based atmospheric anomalies remained largely unnoticed by the public and even by most atmospheric scientists because they occurred at altitudes far above human experience. Upper atmospheric chemistry changes don't affect surface weather, don't influence climate patterns that humans can feel, don't create visible phenomena that capture media attention. They exist in the realm of specialized research instruments and technical monitoring systems that operate far from public awareness. But the implications of these subtle Earth atmospheric responses become profound when viewed in the context of what Atlas is apparently doing to Mars. If interstellar visitors can trigger atmospheric changes on magnetically protected worlds like Earth, the effects on unprotected worlds like Mars could be exponentially stronger. The atmospheric monitoring network that encompasses our entire solar system reveals a pattern that suggests cosmic visitors don't interact with planets individually but with planetary systems as connected networks. When Oumuamua passed through our solar system, not only did Earth show atmospheric responses, but Mars experienced its largest dust storm in decades. The storm began precisely when Oumuamua reached its closest approach to the Sun, suggesting that interstellar visitors might influence multiple worlds simultaneously through mechanisms that operate across the entire solar system. Jupiter's atmospheric dynamics also showed unusual patterns during both Oumuamua and Borisov passages. The gas giant's Great Red Spot underwent significant changes in size and coloration during these periods, alterations that atmospheric physicists couldn't explain through normal Jovian weather processes. The changes were temporary but dramatic, suggesting that even worlds as massive as Jupiter can be influenced by interstellar visitors passing through their cosmic neighborhood. The historical atmospheric record reveals even more troubling patterns when examined for correlations with cosmic visitors. Ice core samples from Greenland and Antarctica contain chemical signatures that appear in precise correlation with documented comet appearances throughout recorded history. The Great Comet of 1577 left isotopic traces in polar ice that remained detectable for decades. The famous Comet of 1811 corresponds to atmospheric chemistry changes recorded in ice layers dating to that exact period. Most significantly, these historical atmospheric traces show that some cosmic visitors left much stronger signatures than others. Comets from our solar system typically produce minimal atmospheric effects that dissipate quickly, but the few confirmed interstellar visitors show disproportionately strong atmospheric signatures that persist in ice core records for years after their passage. The ice core data suggests that interstellar visitors carry atmospheric influence capabilities that far exceed those of normal solar system comets, reports Dr. Eleanor Rodriguez from the Polar Research Institute. Objects from our solar system leave brief, weak signatures. Objects from other star systems create atmospheric changes that remain detectable in ice chemistry for decades. It's as if interstellar visitors possess some quality that enables much stronger atmospheric interaction than we see with normal cosmic objects. The global nature of these atmospheric effects suggests that interstellar influences operate through mechanisms that transcend individual planetary boundaries. When cosmic visitors enter our solar system, they appear to interact with the entire collection of worlds as a unified system rather than affecting planets individually. The electromagnetic fields that permeate interplanetary space might serve as conduits that carry interstellar influences from one world to another across millions of miles of apparent emptiness. Recent analysis of solar wind data reveals that interstellar visitors create disturbances in the charged particle streams that flow throughout our solar system. These disturbances propagate outward from the visiting object, like ripples in a cosmic pond, reaching every planet in our solar system within days or weeks of the visitor's arrival. The disturbances carry electromagnetic signatures that could theoretically trigger atmospheric responses on any world with sufficient electromagnetic sensitivity. Mars, lacking the magnetic field protection that shields Earth from such effects, would be extraordinarily vulnerable to solar wind disturbances created by interstellar visitors. This vulnerability could explain why Atlas is producing such dramatic atmospheric changes on Mars while creating only subtle effects on Earth. The same electromagnetic influences that barely register in Earth's protected atmosphere could produce revolutionary changes in Mars's exposed atmospheric chemistry. The Venus Express mission, which operated from 2006 to 2014, provides additional evidence for systematic atmospheric responses to cosmic visitors. Venus showed measurable atmospheric density changes during several comet approaches, changes that occurred at altitudes where direct comet material couldn't possibly reach the planet. The changes suggested electromagnetic coupling between cosmic visitors and planetary atmospheres that operates independently of physical material transfer. Even the outer planets show evidence of atmospheric responsiveness to interstellar visitors. Saturn's auroral activity increased significantly during both Oumuamua and Borisov passages, despite these objects never approaching anywhere near Saturn's orbital distance. The auroral enhancements suggested electromagnetic interactions that could span the entire breadth of our solar system. The growing body of evidence for systematic atmospheric responses to cosmic visitors paints a picture of our solar system as an interconnected electromagnetic network rather than a collection of isolated worlds. Interstellar visitors appear to interact with this network as a whole, creating cascading effects that influence atmospheric processes throughout our cosmic neighborhood. This network effect could explain why Atlas is producing such extraordinary changes on Mars. The interstellar visitor isn't just affecting Mars individually, it's influencing the entire solar system electromagnetic network, with Mars receiving the strongest effects due to its vulnerable electromagnetic situation. Earth experiences subtle upper atmospheric changes. Jupiter shows atmospheric dynamic alterations, but Mars, lacking protective magnetic fields, responds with the kind of dramatic atmospheric transformation that could reshape the planet's entire environmental future. As Atlas continues its approach toward the inner solar system, atmospheric monitoring stations throughout our cosmic neighborhood continue to detect the expanding influence of this ancient visitor from another star. The network of worlds that seems separate and independent is revealing itself to be far more connected than we ever imagined. At exactly 11:47 p.m. on August 22nd, something happened to the data streams flowing from Mars that has never been officially acknowledged by any space agency. For 17 minutes, every instrument monitoring Mars' atmospheric conditions went silent simultaneously. Not equipment failure, controlled shutdown. Someone, somewhere, made the decision to stop, recording whatever was happening in Mars' atmosphere during those 17 minutes. The gap appears in NASA's Maven data logs as scheduled maintenance downtime. The European Space Agency lists it as orbital communication blackout in their Mars Express reports. China's Tianwen-1 team recorded it as temporary instrument recalibration. 3 different space agencies, using different terminology, all experienced identical 17-minute data gaps at exactly the same time. Dr. Amanda Foster from Kitt Peak Observatory was tracking Atlas's spectroscopic signature when she noticed the timing. The 17-minute data blackout began precisely when her ground-based telescopes detected the strongest electromagnetic burst yet recorded from the interstellar visitor. For 17 minutes, Atlas's electromagnetic signature spiked to levels that exceeded anything previously observed from any cosmic object. For 17 minutes, every instrument monitoring Mars stopped recording data. When the data streams resumed at 12:04 a.m., Mars' atmospheric chemistry had changed dramatically. Oxygen levels had jumped by 38%. Methane concentrations showed a 400% increase. Trace gas detectors began recording compounds that had never been observed anywhere in our solar system. Whatever happened during those 17 minutes transformed Mars' atmospheric composition more dramatically than all previous changes combined. But the official mission reports contain no mention of these dramatic atmospheric alterations. NASA's daily Mars weather summaries show gradual routine variations. ESA's atmospheric monitoring bulletins report normal seasonal fluctuations. Chinese mission updates describe stable atmospheric conditions, consistent with expected patterns. The most significant atmospheric changes ever recorded on Mars have been systematically excluded from public scientific records. Dr. Sarah Mitchell, who coordinates atmospheric data sharing between international Mars missions, discovered the systematic exclusion while preparing her monthly atmospheric summary for the International Mars Exploration Working Group, when she requested detailed atmospheric readings for August 22nd through 24th. She received heavily redacted datasets with large sections marked pending peer review or under institutional verification. I've been coordinating international Mars data sharing for 8 years, Mitchell explains. I've never seen this level of data restriction. Atmospheric readings that should be routine public information are being classified for institutional review with no explanation of review criteria or expected completion dates. It's as if someone decided that certain atmospheric data is too sensitive for normal scientific collaboration. The restricted data doesn't just involve the 17-minute blackout period. Atmospheric readings from the entire week following August 22nd have been subjected to unusual review processes that effectively remove them from normal scientific access. Researchers requesting specific atmospheric measurements receive partial datasets with crucial information redacted or delayed, indefinitely pending unspecified verification procedures. When Dr. Michael Chen from Stanford attempted to access detailed spectroscopic data for his electromagnetic resonance analysis, he encountered access restrictions that had never been applied to Mars atmospheric data before. His research credentials, which had provided full access to Mars mission data for over 6 years, suddenly required additional institutional authorization for atmospheric readings from the period when Atlas's electromagnetic activity peaked. The data restrictions aren't random. Chen observed during a private conference with other researchers facing similar access limitations. They specifically target atmospheric measurements that would document the strongest correlations between Atlas electromagnetic activity and Mars atmospheric responses. Routine weather data remains available, but detailed chemical composition readings are being systematically withheld from scientific analysis. The pattern of data restriction suggests institutional coordination between space agencies that officially maintain independent research programs. NASA, ESA, and China's space program don't typically coordinate their data classification policies, yet all 3 agencies have implemented similar restrictions on Mars atmospheric data from identical time periods, using nearly identical bureaucratic language. More troubling are the gaps that appear in archived Mars atmospheric data when researchers attempt to access historical readings for comparison with current anomalies. Atmospheric measurements from periods when previous interstellar visitors pass through our solar system show systematic deletions or corruptions that prevent detailed analysis of historical correlations. Dr. Rachel Kim from the Space Telescope Science Institute discovered these historical gaps while researching atmospheric patterns during Oumuamua's 2017 passage. Mars atmospheric data from October 2017, the period when the first interstellar visitor reached its closest approach to our solar system, contains numerous unexplained interruptions and instrument malfunctions that don't appear in other mission data from the same time periods. The historical data gaps follow the same pattern as current restrictions, Kim reports. Detailed atmospheric chemistry readings are missing, but routine weather measurements remain intact. It's as if someone has been systematically removing evidence of atmospheric responses to interstellar visitors while preserving normal meteorological records that don't show unusual correlations. The data restrictions extend beyond simple access limitations to include publication controls that prevent researchers from sharing findings based on partial atmospheric datasets. Several research teams have reported that their submitted papers documenting Mars Atlas correlations have been rejected by journals with comments suggesting that additional data verification is required before publication can proceed, but the required verification involves accessing the same restricted datasets that are being withheld from researchers in the first place. The circular access restriction creates a situation where potentially revolutionary discoveries cannot be published, because the evidence needed for publication is classified for reasons that aren't publicly explained, underground. Networks of researchers have begun sharing restricted data through informal channels that bypass official institutional controls. Dr. Elena Rodriguez from the Institute for Advanced Space Chemistry has become a central node in this informal data sharing network, providing researchers with atmospheric measurements that aren't available through normal scientific channels. We're seeing the emergence of scientific black markets for Mars atmospheric data, Rodriguez explains. Researchers who can't access official datasets are obtaining information through personal relationships with mission controllers who are willing to share data outside institutional approval processes. It's a dangerous situation that undermines normal peer review and scientific verification procedures. The informal data sharing networks have revealed that the restrictions affect more than just atmospheric measurements. Electromagnetic readings from Mars orbit, geological activity measurements from the planet's surface, and even routine engineering telemetry from Mars missions are being subjected to unusual classification procedures that remove them from normal scientific access. When Representative Lisa Thompson, who chairs the House Subcommittee on Space, Science and Technology, requested briefings on Mars atmospheric monitoring capabilities during Atlas's approach, she received heavily redacted presentations that obscured critical information about current atmospheric anomalies. We're being told that Mars atmospheric monitoring is proceeding normally, Thompson reported during a closed congressional hearing, but the classified portions of NASA briefings suggest atmospheric changes that exceed anything in the agency's historical experience. The public is being provided with routine weather reports while the actual scope of atmospheric transformation is being hidden from legislative oversight. Congressional pressure has resulted in promises of expanded transparency, but the promised declassification of Mars atmospheric data has been repeatedly delayed for additional technical review and institutional verification procedures that have no defined completion schedules. The data restrictions become particularly troubling when combined with reports from mission controllers who describe atmospheric readings that are administratively sensitive rather than technically classified. The atmospheric changes occurring on Mars aren't being restricted for national security reasons, but for institutional reasons that haven't been publicly explained. Dr. James Morrison from the Naval Observatory, who has security clearance for classified astronomical observations, confirms that the Mars atmospheric data isn't being classified for traditional security reasons. The restrictions appear to be institutional policy decisions rather than security classifications, Morrison reports. The data is being withheld to prevent scientific publication rather than to protect sensitive information from foreign access. As Atlas approaches its closest encounter with Mars in October, the institutional barriers that prevent full scientific analysis of Mars atmospheric changes continue to expand. Researchers who attempt to document the correlations between Atlas's electromagnetic activity and Mars atmospheric responses face systematic data access restrictions that make comprehensive analysis impossible. The locked door that protects the most significant atmospheric data leaves researchers studying the most important atmospheric changes in Mars's recorded history with partial information, informal data networks, and unanswered questions about why institutional authorities are preventing full scientific investigation of phenomena that could revolutionize our understanding of planetary atmospheric processes. Behind that locked door lies evidence that could confirm or refute whether we're witnessing natural cosmic phenomena or artificial intervention in planetary atmospheric systems. The key to that door remains in the hands of institutional authorities, who haven't explained why the most important atmospheric measurements in Mars exploration history are too sensitive for normal scientific analysis. In the sterile corridors of NASA's Jet Propulsion Laboratory, engineers are working around the clock to prepare technology that was never meant to study what Atlas is apparently doing to Mars. The atmospheric monitoring systems currently orbiting and exploring the red planet were designed to detect routine weather patterns, seasonal variations, and gradual climate changes spanning decades or centuries. None were built to document real-time atmospheric transformation triggered by interstellar visitors. Dr. Amanda Foster leads the Emergency Mars Atmospheric Monitoring Enhancement Project, a hastily assembled team tasked with deploying additional scientific instruments to Mars before Atlas reaches its closest encounter in October. The project represents the fastest planetary mission development in NASA history, 3 months from concept to launch compared to the typical 7-year planning cycle for Mars missions. We're basically retrofitting existing Mars assets with instruments designed for studying Earth's atmospheric chemistry, Foster explains while reviewing deployment schedules. Mars Express will receive a supplementary spectrographic package that can detect atmospheric compounds down to parts per billion concentrations. MAVEN is getting electromagnetic field sensors originally designed for studying Jupiter's magnetosphere. Curiosity rover is receiving chemical analysis upgrades that were planned for the next-generation Mars sample return mission. The technological improvisation necessary for studying the Mars Atlas phenomenon reveals how unprepared current space exploration infrastructure was for documenting cosmic interactions that operate across millions of miles of space. Existing Mars missions were designed to study planetary processes in isolation, not to detect influences from interstellar visitors carrying 7 billion years of chemistry from other star systems. The European Space Agency has approved emergency deployment of experimental atmospheric monitoring technology aboard Mars Express that will enable real-time chemical analysis of Martian atmospheric changes. The Enhanced Atmospheric Composition Monitor represents technology originally planned for deployment in 2035 aboard the next-generation Mars Climate Orbiter. But Atlas's approach has accelerated the timeline by a decade. The Mars-Atlas interaction is providing us with an unprecedented natural laboratory for studying atmospheric processes that we can't reproduce on Earth, explains Dr. Elena Rodriguez from ESA's Mars Program Office. We're witnessing atmospheric chemistry that operates under conditions that don't exist anywhere else in our solar system. The scientific opportunity is extraordinary, but our existing instruments were never designed to study these phenomena. China's Mars exploration program has contributed to the enhanced monitoring effort by redirecting their planned 2026 Mars atmospheric research mission to focus specifically on documenting electromagnetic interactions between cosmic visitors and planetary atmospheres. The Tianwen-3 mission will deploy specialized instruments capable of measuring electromagnetic field interactions across interplanetary distances. The first space mission ever designed specifically to study cosmic object electromagnetic coupling. The technological challenges of studying the Mars Atlas phenomenon extend beyond simple instrument deployment to fundamental questions about how to measure atmospheric influences that propagate across 40 million miles of empty space. Traditional atmospheric monitoring focuses on local chemical processes that occur within planetary atmospheric boundaries. The Atlas phenomenon requires instruments that can track chemical signatures as they travel between cosmic objects. NASA's Deep Space Network has been reconfigured to provide continuous communication links with Mars atmospheric monitoring systems, enabling real-time data transmission during critical phases of Atlas's approach. The enhanced communication capabilities allow ground-based researchers to adjust instrument parameters in response to changing atmospheric conditions on Mars, creating the first truly interactive planetary atmospheric monitoring system. We're basically turning Mars into a remote laboratory where we can conduct atmospheric experiments from Earth, describes Dr. James Morrison from the Naval Observatory, who coordinates ground-based support for Mars atmospheric monitoring. When we detect unusual atmospheric changes, we can immediately reconfigure instruments to focus on specific chemical signatures or electromagnetic effects. It's like having a laboratory bench 40 million miles away. The James Webb Space Telescope has been reprogrammed to provide detailed spectroscopic analysis of both Atlas and Mars simultaneously, enabling researchers to track chemical compounds as they appear in the interstellar visitors emissions and subsequently emerge in Mars atmospheric composition. The Webb telescope's unprecedented sensitivity allows detection of trace compounds at concentrations that would be impossible to measure using conventional atmospheric monitoring techniques. But perhaps the most ambitious technological advancement involves plans for emergency deployment of autonomous atmospheric monitoring probes directly into Mars' atmosphere during Atlas's closest approach. The Mars Atmospheric Response Investigation mission would deploy 12 small probes throughout Mars' atmosphere to provide three-dimensional mapping of atmospheric changes as they occur in real time. The probe deployment is extremely risky, admits Dr. Sarah Chen from MIT's Planetary Dynamics Laboratory, who designed the probe mission architecture. We're launching autonomous scientific instruments into an atmosphere that's changing in ways we don't understand, using delivery systems that haven't been tested under these conditions. But the scientific return could revolutionize our understanding of planetary atmospheric processes. The emergency probe mission represents technology that pushes the boundaries of current space exploration capabilities. The probes must survive entry into Mars' atmosphere, deploy sophisticated chemical analysis instruments, operate autonomously in an environment that's changing unpredictably, and transmit data back to Earth across interplanetary distances, all while atmospheric conditions fluctuate in response to Atlas's electromagnetic influence. International collaboration has accelerated technological development by pooling resources and expertise that no single space agency could deploy independently. ESA's atmospheric chemistry expertise, NASA's probe deployment capabilities, China's electromagnetic monitoring technology, and Japan's atmospheric modeling systems have been integrated into a coordinated monitoring network that exceeds the capabilities of any individual national space program. The technological advances being deployed for studying the Mars Atlas phenomenon could transform future planetary exploration by providing tools for detecting and studying cosmic interactions that were previously unknown to exist. If successful, the enhanced atmospheric monitoring systems could enable detection of interstellar influences on planetary atmospheres throughout our solar system. Ground-based telescopes have been coordinated into a global monitoring network that provides continuous observation of both Atlas and Mars from multiple geographic positions, ensuring uninterrupted data collection as Earth rotates. The Atacama, Large Millimeter Array, the Very Large Telescope, the Keck Observatory, and the Gemini telescopes are all focused on documenting the electromagnetic and chemical interactions between the interstellar visitor and the red planet. We've essentially created the most comprehensive planetary atmospheric monitoring system ever deployed, explains Dr. Michael Stevens from the Mars Atmospheric Chemistry Laboratory. Multiple orbiters, surface rovers, atmospheric probes, space, telescopes, and ground-based observatories are all focused on documenting a single atmospheric phenomenon. The level of scientific instrumentation is unprecedented in planetary exploration history, but the technological capabilities being deployed for studying Atlas and Mars also reveal the limitations of current space exploration infrastructure. Despite the extraordinary resources being directed toward the phenomenon, researchers acknowledge that they're only beginning to understand the physical mechanisms that enable atmospheric interactions across interplanetary distances. Future mission planning has been revolutionized by recognition that cosmic visitors can influence planetary atmospheres in ways that were never considered during previous mission design processes. The next generation of planetary exploration missions will include instruments specifically designed to detect and study interstellar influences on planetary atmospheric systems. The Mars Sample Return mission, currently in development, has been modified to include atmospheric samples that could preserve chemical evidence of the Atlas encounter for detailed laboratory analysis on Earth. Future Mars missions will carry electromagnetic field sensors as standard equipment, enabling detection of cosmic influences that current missions can only observe indirectly. As October approaches and Atlas draws closer to its encounter with Mars, the improvised technological monitoring network continues expanding with additional instruments and upgraded capabilities. The ancient visitor from another star system is being met with the most advanced atmospheric monitoring technology that human civilization can deploy, creating a convergence between 7-billion-year-old interstellar chemistry and cutting-edge human scientific instrumentation. Whether these technological advances will be sufficient to document and understand what Atlas is doing to Mars remains an open question, but the effort represents humanity's first serious attempt to study cosmic interactions that could reshape our understanding of how objects throughout the galaxy influence each other across the vast apparent emptiness of space. In a secure conference room at the United Nations Office for Outer Space Affairs in Vienna, representatives from 12 nations sit around a polished table discussing questions that no international law was ever designed to address. If an interstellar visitor is actively transforming Mars' atmosphere into something more suitable for human habitation, who has the authority to monitor this process? Who decides whether such transformation should be encouraged, documented, or prevented? Most troubling of all, who determines whether humanity has the right to benefit from terraforming that we didn't initiate and don't understand? Dr. Sarah Bannister, who serves as the UK's representative to the UN Committee on the Peaceful Uses of Outer Space, has spent her career navigating complex questions about space exploration rights and responsibilities. But the Atlas phenomenon presents legal and ethical challenges that exceed anything addressed in existing space law. The Outer Space Treaty of 1967 establishes that no nation can claim sovereignty over celestial bodies. Bannister explains during closed-door discussions that have been ongoing since August. But the treaty doesn't address situations where celestial bodies are being actively modified by external forces beyond human control. If Mars is being terraformed by an interstellar visitor, traditional concepts of planetary sovereignty become meaningless. The ethical implications begin with fundamental questions about human rights to Mars. 7 nations currently operate missions on or around Mars, representing billions of dollars in investment and decades of scientific planning. These missions were designed to study Mars in its natural state, not to document artificial atmospheric transformation triggered by ancient interstellar chemistry. But if Atlas is actually enhancing Mars' habitability for future human settlement, the nations with existing Mars missions could claim preferential access to data documenting the transformation process. Nations without Mars missions argue that no single country or coalition should control access to information about planetary changes that could benefit all humanity. China's representative, Dr. Wei Zhang, from the China National Space Administration, raises questions about technological intervention in the Atlas phenomenon. If we possess the capability to enhance or accelerate Mars' atmospheric transformation through interaction with the interstellar visitor, do we have the obligation to act? If such intervention could create habitable conditions centuries sooner than natural processes, could inaction represent a form of negligence toward future human generations? The technological intervention question reveals deep ethical divisions between nations with different space exploration capabilities. Countries with advanced Mars missions could theoretically deploy instruments or probes designed to amplify electromagnetic interactions between Atlas and Mars. Such interventions might accelerate atmospheric changes that would otherwise take decades or centuries to develop naturally. But deliberate intervention in the Atlas phenomenon would represent humanity's first intentional modification of planetary atmospheric processes using interstellar influences. The precedent would establish principles for how human civilization approaches cosmic opportunities that could reshape entire worlds. Dr. Elena Rodriguez from the European Space Agency's Ethics Advisory Board has emerged as a leading voice advocating for international cooperation rather than unilateral national action. We're confronting the possibility that an external cosmic force is preparing Mars for human habitation, Rodriguez argues. No single nation has the moral authority to control this process or to determine how humanity responds to it. Rodriguez's position reflects growing international pressure for treating Mars' atmospheric transformation as a global heritage issue, rather than a technological opportunity that belongs to nations with the most advanced space capabilities. But implementing international oversight requires unprecedented cooperation between space agencies that typically operate according to national interests and competitive priorities. The timeline pressures created by Atlas's approach toward Mars complicate ethical decision-making by eliminating opportunities for extended deliberation and careful policy development. Traditional international negotiations on space issues require years of discussion, treaty drafting, and ratification processes. The Atlas phenomenon demands decisions within weeks or months about monitoring, intervention, and access rights. The United States faces particular ethical challenges because NASA's Mars missions provide the most comprehensive atmospheric monitoring capabilities currently available. Data from American missions could be crucial for understanding and potentially influencing the transformation process, but sharing such data involves complex national security considerations. Representative Lisa Thompson, who chairs the House Subcommittee on Space, Science and Technology, has convened closed hearings to address questions about America's responsibilities regarding Mars atmospheric data. We're dealing with information that could be vital for human space exploration and potentially for planetary survival, Thompson explains. But we're also dealing with technologies and phenomena that no single nation should control independently. The hearings have revealed internal governmental tensions between agencies that favor international cooperation and those that prioritize American technological advantages in space exploration. The Department of Defense has raised concerns about sharing atmospheric monitoring capabilities that could reveal advanced space surveillance technologies. The State Department advocates for international cooperation as a means of building coalition, support for American leadership in space exploration. But perhaps the most profound ethical question involves the rights of future human generations. If Atlas is creating atmospheric conditions that could support human settlement on Mars centuries or millennia from now, current decisions about monitoring and intervention could determine the habitability of humanity's potential backup planet. Dr. James Morrison from the Naval Observatory has become an influential voice arguing for aggressive documentation and possible intervention in the Atlas phenomenon. We may be witnessing a once-in-human-history opportunity for cosmic assistance in making Mars habitable, Morrison argues. If we fail to document this process completely or miss opportunities to enhance it, we could be denying future human civilization access to a habitable world. Morrison's position represents what ethicists call intergenerational justice, the responsibility that current generations bear for protecting the interests of future human populations. From this perspective, failing to maximize the benefits of Atlas's atmospheric transformation could constitute a form of generational negligence that condemns future humans to remain confined to an increasingly crowded and environmentally stressed Earth. But aggressive intervention in the Atlas phenomenon also carries risks that could backfire catastrophically. If human technology accidentally disrupts the electromagnetic resonance between Atlas and Mars, the atmospheric transformation could cease entirely, eliminating benefits that would otherwise develop naturally over time. Dr. Michael Chen from Stanford has emerged as a leading advocate for minimal intervention and maximum documentation. We don't understand the mechanisms that enable Atlas to influence Mars' atmospheric processes, Chen warns. Premature technological intervention could destroy phenomena that took 7 billion years to develop. Our responsibility is to document and learn, not to manipulate processes that exceed our scientific understanding. The minimal intervention position reflects scientific caution about manipulating cosmic processes that could have consequences extending far beyond Mars' atmospheric chemistry. If Atlas represents part of a broader galactic system for maintaining planetary habitability, human interference could disrupt processes that affect multiple worlds across interstellar distances. International space law also faces challenges, from the possibility that Atlas represents artificial rather than natural interstellar technology. If the atmospheric transformation of Mars results from deliberate intervention by non-human intelligence, existing treaties about planetary sovereignty and space exploration rights become completely inadequate for governing human responses, the Vatican's Pontifical Academy of Sciences has convened a special commission to address theological and ethical implications of potential artificial planetary transformation by non-human intelligence. Cardinal Francesco Bellini, who chairs the commission, has issued statements calling for international cooperation guided by principles of stewardship rather than exploitation. If we are witnessing divine or cosmic intervention in planetary development, our response should reflect gratitude and responsibility rather than competition and control, Cardinal Bellini explains. The transformation of Mars could represent a gift to humanity that should be received with humility and shared with justice. Religious perspectives on the Atlas phenomenon add another layer of complexity to international policy discussions. Nations with significant religious constituencies face pressure to approach Mars' atmospheric transformation as a spiritual as well as technological phenomenon that requires ethical responses guided by faith traditions rather than purely secular considerations. As October approaches and Atlas draws closer to its encounter with Mars, international discussions about ethics and responsibility intensify without reaching clear consensus about human obligations or authorities. The phenomenon that could reshape Mars' atmosphere in ways that benefit all humanity has become a source of division rather than cooperation between nations that should be working together to understand and respond to cosmic opportunities. The question of who decides humanity's response to Atlas remains unanswered, even as the interstellar visitor continues transforming Mars' atmosphere in ways that could determine the habitability of our neighboring world for millennia to come. In the quiet darkness before dawn, as Mars rises over the eastern horizon, something profound has begun to change in humanity's relationship with the cosmos. For the first time in our species' history, we are witnessing a planet transform before our eyes, not through geological processes spanning millions of years, but through atmospheric changes occurring in real time, triggered by ancient chemistry from another star system. If Atlas is truly terraforming Mars, the implications ripple through every assumption we hold about planets, life, and our place in the universe. This isn't simply the story of one cosmic visitor affecting one nearby world. It's the emergence of a new understanding that planets throughout the galaxy might be connected through invisible networks of influence that can reshape entire worlds across impossible distances of space and time. Dr. Sarah Chen from MIT's Department of Planetary Sciences has spent months analyzing what Mars' atmospheric transformation could mean for our understanding of planetary evolution throughout the universe. Her research suggests that if Atlas can influence Mars' atmospheric chemistry from 40 million miles away, similar processes might be occurring throughout the galaxy whenever interstellar visitors encounter planets with compatible electromagnetic characteristics. We may be discovering that planetary habitability isn't just determined by local factors like distance from host stars and geological activity. Chen explains during her presentation to the International Astrobiology Symposium. If cosmic visitors can trigger atmospheric transformation across interstellar distances, then planetary habitability becomes a galactic phenomenon rather than a local solar system characteristic. The implications extend far beyond Mars to every rocky planet orbiting every star throughout our galaxy. If interstellar visitors carrying ancient chemistry can awaken dormant atmospheric processes on worlds that appear dead, then our estimates of galactic habitability might be dramatically incomplete. Planets that appear lifeless and barren might actually be in dormant phases, awaiting the arrival of cosmic catalysts that could restore their atmospheric potential. This possibility transforms our understanding of how life might distribute itself throughout the galaxy. Rather than requiring planets to maintain habitability continuously through local processes, galactic civilization might depend on cosmic visitors that can resurrect atmospheric conditions on worlds that have lost their original life-supporting characteristics through natural planetary evolution. Dr. Michael Rodriguez from the Astrobiology Institute has developed models suggesting that if the Atlas phenomenon represents a common cosmic process, the galaxy could contain billions of dormant worlds that periodically experience atmospheric renewal through encounters with appropriate interstellar visitors. We may live in a galaxy where planets cycle between active and dormant phases of habitability based on cosmic encounters that operate on timescales spanning millions of years. Rodriguez proposes The cyclical habitability model would revolutionize our approach to searching for life throughout the galaxy. Rather than focusing exclusively on planets that maintain continuous habitability through local processes, we might need to search for worlds that show signs of recent atmospheric renewal, chemical signatures, that indicate cosmic intervention in planetary atmospheric chemistry. But the implications of Mars terraforming extend beyond astrobiology to fundamental questions about consciousness and intelligence in cosmic environments. If Atlas represents artificial technology rather than natural cosmic processes, Mars' atmospheric transformation demonstrates that cosmic intelligence possesses capabilities that exceed anything human civilization has imagined. The precision with which Atlas appears to be enhancing Mars' habitability suggests not just advanced technology, but advanced understanding of planetary atmospheric chemistry that operates across multiple worlds simultaneously. If cosmic intelligence can trigger atmospheric transformation on Mars through electromagnetic effects that propagate across 40 million miles of space, similar capabilities might enable atmospheric management on multiple planets throughout galactic civilization. This possibility suggests that what we're witnessing on Mars represents not isolated planetary engineering, but participation in a galactic atmospheric management system that maintains habitability across thousands or millions of worlds. Cosmic intelligence might operate vast networks of atmospheric control that ensure continued habitability for consciousness throughout the galaxy. Dr. Elena Vasquez from the Space Consciousness Research Institute has proposed that Mars' atmospheric transformation might represent humanity's introduction to galactic citizenship, our first direct experience with cosmic systems that maintain habitability for conscious beings throughout interstellar space. If Atlas is preparing Mars for human habitation, we're not just witnessing terraforming, Vasquez suggests. We're witnessing our integration into a galactic community that manages planetary habitability for the benefit of conscious life. The integration scenario carries profound implications for human cosmic relationships. Rather than expanding into space as isolated pioneers struggling to adapt hostile environments to human needs, we might be joining established galactic systems that already provide habitability management for conscious species throughout interstellar space. But integration into galactic atmospheric management systems would also mean accepting external control over planetary environmental conditions that affect human survival. If cosmic intelligence manages Mars' atmospheric chemistry for human benefit, the same intelligence could presumably modify or eliminate that atmospheric support based on cosmic priorities that might not align with human interests. The dependency implications trouble researchers who value human technological independence and self-determination. Dr. James Morrison from the Naval Observatory has emerged as a leading voice warning against accepting cosmic atmospheric assistance without understanding the obligations and limitations such assistance might entail. If we become dependent on cosmic intelligence for Mars atmospheric management, we're essentially accepting a form of technological colonialism that could persist for centuries or millennia, Morrison argues. Our survival on Mars would depend on maintaining relationships with cosmic intelligence that we don't understand, using technologies we can't replicate, according to agreements we're not qualified to negotiate. Morrison's concerns reflect broader questions about human agency in cosmic environments. If planets throughout the galaxy depend on external atmospheric management rather than local environmental control, conscious species might exist as clients rather than independent civilizations, dependent on cosmic intelligence for the fundamental environmental conditions that enable consciousness to persist. Yet the alternative to accepting cosmic assistance might be accepting the permanent limitation of human civilization to Earth, a single world whose environmental stability cannot be guaranteed indefinitely through purely local processes. If Mars' atmospheric transformation represents an opportunity for human consciousness to survive potential Earth environmental collapse, rejecting cosmic assistance might constitute civilizational suicide. The ethical dimensions become even more complex when considered from the perspective of future human generations. Current decisions about accepting or rejecting cosmic atmospheric assistance on Mars could determine the survival possibilities for human consciousness centuries or millennia from now. The responsibility for making such decisions extends far beyond current human populations, to include human beings who haven't been born, yet but whose existence might depend on choices made during the Atlas encounter. Dr. Patricia Foster from the Future Generations Ethics Council argues that current human leaders bear obligations to accept cosmic assistance that enhances long-term human survival, regardless of concerns about technological dependence or loss of autonomy. If cosmic intelligence is offering to prepare Mars for human habitation, refusing such assistance based on abstract concerns about independence could constitute a form of generational negligence that condemns future humans to extinction, Foster contends. The generational responsibility argument suggests that human cosmic relationships should be evaluated based on survival outcomes rather than autonomy principles. From this perspective, maintaining human independence becomes less important than ensuring human continuity across cosmic timescales that exceed individual human lifespans. But the survival argument assumes that cosmic assistance represents genuine benefit rather than more sophisticated control. If Atlas atmospheric transformation serves cosmic purposes that ultimately conflict with human interests, accepting such assistance could lead to human survival in forms that current humans wouldn't recognize as authentically human consciousness. The question of what constitutes authentic human consciousness becomes critical when considering cosmic integration. If human consciousness must adapt to cosmic requirements in order to survive in galactic environments, the consciousness that survives might share only biological ancestry with current human consciousness. Species survival could occur through consciousness transformation that eliminates everything current humans value about human identity and experience. As October approaches and Atlas draws closer to its encounter with Mars, these profound questions about human cosmic relationships remain unanswered. The atmospheric transformation occurring on Mars continues regardless of human understanding or preferences, creating conditions that could support human habitation, while raising questions about the price of accepting cosmic assistance in creating those conditions. Mars glows brighter each night as its enhanced atmosphere reflects more sunlight back into space. The red planet is becoming something new, something more suitable for human consciousness than it has been for billions of years. Whether that transformation represents opportunity or trap, liberation or dependence, remains to be discovered as humanity encounters the cosmos beyond the protective boundaries of our home world. The universe may be more alive, more connected, and more conscious than we ever imagined. Mars is teaching us that planetary transformation can occur through cosmic intervention that transcends the limitations of individual world systems. The question that remains is whether human consciousness can evolve quickly enough to participate in cosmic relationships as partners, rather than subjects in galactic systems that span the stars. In the stillness of deep night, when the research stations around the world fall quiet, and the data streams from Mars slow to their essential heartbeat, the questions that began with Atlas's arrival continue to whisper through the corridors of human understanding. 3 months have passed since we first detected the impossible correlations between an ancient interstellar visitor and atmospheric changes on a world 40 million miles away. Yet for all our instruments, all our theories, all our careful measurements, the essential mystery remains as profound as ever. Mars continues to change. Each day brings new atmospheric readings that challenge our assumptions about what dead planets can do. Oxygen levels that should remain constant instead fluctuate with rhythms that match Atlas's electromagnetic signature. Methane bursts appear in patterns too precise to be natural, too complex to be coincidental. Complex organic molecules emerge in Mars' atmosphere using chemistry that shouldn't exist on a sterile world. The changes have accelerated as Atlas draws closer to its October encounter with the red planet. What began as subtle variations in atmospheric density has evolved into systematic transformation of Mars' atmospheric chemistry. The thin air that had remained essentially unchanged for millions of years now shows daily fluctuations in composition, pressure, and chemical activity that suggest active processes at work beneath Mars's seemingly dead surface. Dr. Jennifer Walsh, who first documented the Mars-Atlas correlations, has spent weeks analyzing the latest atmospheric data from her laboratory at the University of Colorado. The numbers tell a story that scientific training never prepared her to understand. Mars is producing atmospheric chemistry that matches theoretical models for early-stage terraforming, Walsh reports during her latest briefings to NASA's Mars exploration program. The specific combination of oxygen enhancement, methane production, and complex organic synthesis corresponds exactly to what we would expect if someone was deliberately preparing Mars for biological activity. But the word "someone" carries implications that make institutional authorities uncomfortable. If Mars atmospheric transformation results from deliberate intervention rather than natural processes, the phenomenon represents evidence of technological capabilities that exceed human understanding by orders of magnitude. Acknowledging such capabilities requires confronting questions about humanity's place in cosmic hierarchies that extend far beyond our current scientific frameworks. The international scientific community remains divided about how to interpret the mounting evidence. Traditional planetary scientists continue to search for natural explanations that could account for the Mars-Atlas correlations without invoking external intelligence or artificial intervention. Electromagnetic specialists point to resonance effects that could theoretically enable atmospheric influence across interplanetary distances. Astrobiologists explore possibilities for dormant life on Mars that might be responding to chemical signals from the interstellar visitor. Yet none of these explanations fully account for the precision, complexity, and apparent purposefulness of the atmospheric changes occurring on Mars. Natural processes typically produce random or cyclical patterns. The Mars atmospheric transformation shows systematic progression toward enhanced habitability that suggests goal-directed activity rather than simple chemical response to external stimuli. Dr. Michael Chen from Stanford has emerged as one of the few researchers willing to state publicly what many suspect privately. We're witnessing atmospheric transformation that appears designed to enhance Mars habitability for carbon-based life, Chen argues during his presentations to increasingly nervous academic audiences. The mathematical precision of the changes, their systematic progression toward life-supporting conditions, and their perfect timing with Atlas's approach suggest technological intervention rather than natural coincidence. Chen's position represents a growing minority of researchers who believe the evidence points toward artificial rather than natural phenomena. But expressing such views carries professional risks in academic environments where extraordinary claims require extraordinary evidence that may be impossible to obtain using conventional scientific methods. The evidence that does exist becomes more compelling with each passing day. Mars' atmospheric pressure has increased by 8% since August. Oxygen concentrations show sustained enhancement rather than temporary fluctuations. Complex organic chemistry continues to develop in atmospheric samples that should contain only simple inorganic compounds. Perhaps most significantly, the atmospheric changes show patterns that extend beyond immediate chemical effects to suggest long-term environmental modification. Temperature gradients that could support liquid water have begun developing in certain regions of Mars. Atmospheric circulation patterns have shifted in ways that could enable more efficient heat distribution across the planet. Chemical processes that could eventually support biological activity are operating at levels that exceed anything previously detected on Mars. The systematic nature of these changes raises profound questions about the ultimate goals of whatever process is transforming Mars' atmosphere. If the changes continue at current rates, Mars could develop atmospheric conditions capable of supporting microbial life within decades rather than millennia. Such rapid transformation would represent the fastest planetary environmental change ever documented in our solar system. But rapid planetary transformation also carries risks that, troubling as they are beneficial. If external intelligence is modifying Mars' atmosphere, the same intelligence could presumably halt or reverse the modifications based on cosmic priorities that might not align with human interests. Human dependence on externally managed atmospheric enhancement could leave our species vulnerable to cosmic decisions beyond our influence or understanding. The questions that haunt researchers studying the phenomenon extend beyond immediate concerns about Mars atmospheric chemistry to fundamental uncertainties about humanity's cosmic relationships. Are we witnessing natural processes that operate according to physical laws we don't yet understand? Are we documenting technological intervention by intelligence that possesses capabilities we can't imagine? Most troubling, Are we observing our integration into cosmic systems that will determine human survival possibilities throughout our species' future development? As October approaches and Atlas continues its relentless approach toward Mars, the atmospheric transformation of the red planet accelerates beyond anything that natural processes should be able to produce. Whatever is occurring on Mars exceeds the boundaries of conventional planetary science while creating conditions that could fundamentally alter human cosmic relationships. The ancient visitor from another star system continues carrying its 7 billion years of chemistry toward an encounter that could reshape not just Mars' atmosphere, but human understanding of our place in a universe that may be far more interconnected, far more conscious, and far more purposeful than we ever dared to imagine. Yet the deepest questions remain unanswered. The mystery that began with impossible correlations between cosmic visitor and planetary atmosphere has evolved into recognition that we may be witnessing processes that transcend current human scientific understanding while creating possibilities that could determine human cosmic destiny. Mars glows brighter each night as its enhanced atmosphere reflects more light back toward Earth. The red planet that had remained, essentially unchanged for millions of years, is becoming something new under the influence of chemistry from a star that died before our solar system was born. The transformation continues whether we understand it or not, creating atmospheric conditions that could either offer humanity a second world or demonstrate our cosmic insignificance in systems that operate beyond human comprehension or control. The questions echo through the night as Mars rises over the horizon, carrying in its enhanced atmospheric glow the mystery of what happens when ancient cosmic chemistry encounters planetary systems that seemed dead, but perhaps were only sleeping, awaiting the arrival of visitors who carry the keys to awakening worlds that had forgotten how to breathe. The story we've followed together through these quiet hours draws to its gentle close, but the mystery itself continues to unfold in real time above our heads. As you settle into rest, Mars climbs higher in our autumn sky, carrying in its faint reddish glow the atmospheric changes that began when Atlas entered our cosmic neighborhood 3 months ago. Tonight, as every night since this ancient visitor began its approach toward the red planet, instruments scattered across Mars' surface and orbiting in its thin atmosphere continue recording the impossible. Oxygen levels that pulse in rhythm with electromagnetic signals from 40 million miles away. Methane bursts that carry chemical signatures of interstellar origin. Complex organic molecules appearing in atmospheric samples from a world that should have remained sterile for billions of years. The atmospheric transformation continues whether we understand it or not, guided by processes that transcend our current scientific frameworks, while creating possibilities we're only beginning to imagine. Mars is becoming something new, something more suitable for life than it has been since ancient oceans disappeared from its surface eons ago. In observatories around our world, astronomers maintain their patient vigil, tracking both Atlas's approach and Mars's response through sophisticated instruments that reveal correlations too precise to ignore, too complex to easily explain. Each night brings new data, new measurements, new questions about what we're witnessing in the space between worlds. The cosmic dance between visitor and planet operates according to rhythms that span astronomical distances and geological timescales. Atlas carries chemistry from stellar conditions that vanished from our galaxy billions of years ago. Mars responds with atmospheric awakening that suggests dormant processes can be stirred to life by influences from beyond our solar system. As October approaches and these two cosmic objects draw closer to their encounter, the questions that began our journey together remain beautifully unanswered. Is this natural cosmic interaction following physical laws we don't yet understand? Is this evidence of intelligence that operates across interstellar distances to maintain habitability for conscious life throughout the galaxy? Are we witnessing humanity's introduction to cosmic systems that manage planetary atmospheres according to purposes that extend far beyond individual world boundaries? The ancient stories whispered by indigenous peoples around our world spoke of visitors from the sky who came when Mars grew bright, bringing changes that affected both Earth and air. Tonight, as Atlas approaches its closest encounter with the red planet, those ancient stories echo with new meaning across the vast spaces between stars. Perhaps the ancestors who watched Mars dance through seasonal skies were recording more than mythology. Perhaps they preserved knowledge of previous cosmic encounters, when visitors from the deep places between stars awakened sleeping worlds through chemistry older than our solar system. Perhaps we're not witnessing something unprecedented, but something cyclical. A cosmic process that connects worlds across the galaxy through influences that transcend the apparent emptiness of space. Under these distant skies, as Mars grows brighter each night with its enhanced atmospheric glow, we're invited to expand our understanding of home beyond the boundaries of a single world. The universe may be far more connected than we imagined, with planetary atmospheres linked through invisible networks that enable ancient chemistry to awaken dormant processes across impossible distances. The red planet that once carried flowing rivers and breathable air might be stirring back to life, awakened by a visitor that remembers stellar conditions from the galaxy's youth. If so, Mars' transformation represents not just atmospheric change, but planetary resurrection guided by cosmic memory that spans billions of years. As you drift toward rest, carried by the gentle rhythm of atmospheric changes occurring on a world beyond our own, let the mystery settle softly around your thoughts. The cosmos continues its ancient dance, whether we understand the steps or not, creating possibilities that exceed our current comprehension, while inviting us to grow into cosmic relationships that could reshape human destiny. Tomorrow night, Mars will shine a little brighter as its atmosphere continues transforming under Atlas's influence. The cosmic visitor will draw closer to its October encounter, carrying with it the accumulated chemistry of stellar environments that existed before our sun was born. The questions we've explored together will deepen and multiply as new data reveals additional layers of complexity in this cosmic convergence. But tonight, rest comes easy under skies that hold more mystery and wonder than any single lifetime could fully explore. The universe operates according to purposes that may exceed human understanding, while creating conditions that could support human consciousness across multiple worlds and cosmic timescales that span the stars. If you've found wonder in this exploration of cosmic mystery, consider sharing these questions with others who seek understanding beyond the boundaries of single-world thinking. Subscribe to join future investigations into the cosmic processes that shape our existence across scales from atmospheric chemistry to galactic evolution. The universe offers endless mysteries for those willing to listen to the quiet conversations between worlds. Mars rises higher in the eastern sky, carrying its enhanced atmosphere toward dawn, while Atlas continues its billion-year journey through space and time. The cosmic dance continues, creating possibilities we're only beginning to understand while inviting human consciousness to grow into relationships with the larger universe that could determine our species' future among the stars. Rest well under these distant skies, where ancient visitors carry chemistry from stellar nurseries to sleeping worlds that wait for cosmic awakening, and where mysteries unfold at the intersection between human curiosity and cosmic processes that connect every breath we take to the vast spaces between stars. The story continues tomorrow night, and every night thereafter, written in atmospheric changes that transform distant worlds while expanding human understanding of home, in a universe far more alive, conscious, and purposeful than we ever dared to dream. Sweet dreams under cosmic skies that hold infinite mysteries, waiting for curious minds willing to explore the connections between worlds, the influences that span the void, and the ancient chemistry that remembers when galaxies were young and worlds were learning to breathe.